For a long time, we have seen movies where space travelers sleep for hundreds of years in icy capsules. It seems like something very simple and safe, like just taking a long nap and waking up somewhere else. But the truth discovered by scientists changed everything we thought about extreme cold. It turns out that the water inside our body turns into sharp crystals when it freezes, which can destroy everything inside. This forced experts to ask a difficult question about how to cheat death itself. Is it possible to stop time in the human body without causing terrible damage? Prepare to sleep while listening to this video. Subscribe to the channel. Leave your like and comment from which part of the world you are watching. Settle down and relax. Let's start. In movies and television shows, suspended animation is often portrayed as a serene and simple, deep sleep. A peaceful pause in life that allows astronauts to travel across the cosmos without aging or suffering. But the biological truth behind freezing a human body is anything but gentle. It is a violent and destructive process that shatters the very foundation of life at a cellular level. This stark contrast between the cinematic dream and the scientific reality is where our understanding of cryonics must begin. When we see characters in science fiction waking up after centuries in frozen slumber, they appear unchanged, ready to continue their adventures as if no time has passed. However, in the real world, uncontrolled freezing leads to irreversible damage that would make reanimation impossible with current technology. The illusion sold by films ignores the fundamental principles of biology and physics that govern living organisms. Our bodies are composed of cells that rely on a delicate balance of water, proteins, and other molecules to function properly. Water, which makes up about 60% of the human body, expands when it freezes, forming sharp, needle-like crystals that pierce through cell membranes, organelles, and blood vessels. This isn't just a minor issue. It is a catastrophic event that reduces complex tissues to a pulverized mess. Imagine a finely tuned engine filled with expanding ice that fractures every component from the inside out. That is what happens during unmanaged freezing. Biological life on Earth has evolved over millions of years to operate within an extremely narrow temperature range, typically around 37 degrees Celsius for humans. Straying even a few degrees outside this range can lead to hypothermia or heat stroke, demonstrating how sensitive our systems are. Pushing the body far below freezing points into the realm of cryogenic temperatures means entering a zone where the normal processes of life cease and destruction takes over. The idea of stopping time for an astronaut in transit sounds appealing, but it disregards the physical and chemical nature of water and biological tissues. In reality, time doesn't stop. Instead, the freezing process initiates a series of damaging events that accumulate until the structure of the body is compromised beyond repair. For instance, when ice crystals form, they not only cause mechanical damage by tearing through cells, but also lead to osmotic stress. As water freezes outside cells, it draws water out from inside the cells through osmosis, causing them to dehydrate and collapse. This double whammy of physical piercing and chemical imbalance ensures that even if the body is thawed, the cells would not survive. This is why simply placing a human in a freezer, as one might preserve food, would result in certain death rather than suspended animation. The dissonance between the popular imagination and the cutting-edge science of cryonics highlights why this field is one of the most complex challenges faced by medical researchers and space engineers today. It isn't just about achieving low temperatures. It is about understanding and mitigating the inherent destructiveness of freezing. In science fiction, the focus is often on the futuristic technology of the pods or the drama of awakening. but rarely on the biological horrors that occur during the process. This oversight can lead to public misconceptions about the feasibility of cryonics for long-duration space travel. For astronauts on missions that could last centuries, finding a way to preserve the body without causing damage is paramount. However, the current reality is that we lack the means to safely freeze and thaw a whole human body without incurring lethal injuries. The challenges begin with the basic properties of water. Water molecules form a crystalline structure when frozen, which expands and takes up more space. In a confined cellular environment, this expansion generates immense pressure, rupturing membranes and disrupting cellular function. Moreover, different tissues freeze at different rates due to variations in water content and density, leading to uneven damage throughout the body. Organs like the brain, which is highly sensitive and complex, would suffer particularly severe harm from ice formation, potentially erasing memories and personality traits. This is a far cry from the peaceful sleep depicted on screen, where characters awaken with their identities intact. The scientific community recognizes that overcoming these obstacles requires more than just advanced cooling systems. It demands a deep understanding of cryobiology, the study of how living organisms respond to cold. Researchers have known for decades that freezing causes cellular damage, but developing solutions has proven incredibly difficult. For example, early experiments with cryopreservation often resulted in tissues that were mushy and non-viable upon thawing, similar to how frozen fruits lose their texture and become watery when defrosted. This analogy helps illustrate the point. Living tissues are not designed to be frozen and thawed like inert objects. They are dynamic, hydrated systems that rely on continuous biochemical processes to maintain integrity. When those processes are halted by freezing, the structural support collapses. Another aspect often overlooked in sci-fi is the role of the circulatory system in freezing. Blood, which carries oxygen and nutrients, would freeze solid, causing vessels to burst and leading to massive internal bleeding upon thawing. This is why cryonics isn't just about individual cells, but about the entire organism as an integrated system. The heart, lungs, brain, and other organs must all be preserved simultaneously, which multiplies the complexity. In movies, these details are glossed over for the sake of narrative simplicity, but in reality, each organ presents unique challenges due to its specific cellular composition and function. For instance, the liver has a high water content and would freeze differently from the bones, which are denser. This lack of homogeneity means that a one-size-fits-all approach to freezing doesn't work. Instead, customized protocols would be needed for different parts of the body, which is currently beyond our capabilities. The importance of addressing this issue for space exploration cannot be overstated. If humanity is to reach distant stars, we need a method to sustain astronauts over journeys that could span generations. Cryonics offers a potential solution, but only if we can solve the fundamental problem of freezing damage. Without this, astronauts would perish long before reaching their destination, making the mission pointless. Thus, the gap between the cinematic illusion and biological reality isn't just a matter of scientific accuracy. It has practical implications for the future of space travel. By acknowledging this dissonance, we can focus research efforts on the real hurdles rather than chasing fictional ideals. This means investing in studies that explore how to prevent ice formation, protect cell membranes, and maintain metabolic arrest without causing harm. While techniques like vitrification aim to address some of these issues by turning tissues into a glass-like state without ice crystals, they are still in experimental stages and come with their own set of challenges. such as toxicity from cryoprotectants. However, staying within the scope of this topic, the key takeaway is that the peaceful frozen sleep of sci-fi is a biological impossibility without groundbreaking advances. The journey to making cryonics a reality for astronauts starts with dispelling the myths and confronting the harsh truths of freezing. It requires a collaborative effort between biologists, engineers, and physicians to unravel the complexities of cellular preservation. In the meantime, every time we see a movie depicting suspended animation, we should appreciate the creativity, but also remember the immense scientific hurdles that remain. This understanding not only fuels innovation, but also sets realistic expectations for what might be achievable in the future. As we continue to explore the cosmos, the dream of freezing astronauts for long voyages serves as a motivator, but it is grounded in the need for rigorous science to turn that dream into reality. The illusion of easy frozen sleep may be compelling, but the reality of biological destruction is what drives the quest for solutions. By bridging this gap, we move closer to enabling humanity's expansion into the universe, one cell at a time. So, having established that the peaceful frozen sleep of science fiction is a biological impossibility, we must now dive into the gritty details of what actually happens when a body freezes. And it all centers on a seemingly innocent substance: water. Water is the essence of life, making up about 60% of our bodies. But during freezing, it becomes a destructive force through the formation of ice crystals. This isn't just about things getting cold and solid. It's a violent physical process where water molecules rearrange into a crystalline structure that expands. And this expansion is where the trouble begins. Imagine a single cell as a tiny, water-filled balloon. When the water inside freezes, it expands. And since the cell membrane is flexible but not infinitely stretchy, the ice crystals push outward, piercing and rupturing the membrane. Now, scale that up to trillions of cells throughout the body, and you can see how freezing turns tissues into a shredded, unrecognizable mess. But the damage doesn't stop at mechanical piercing. As ice forms outside the cells, it draws water out from inside them through a process called osmosis. This happens because the concentration of solutes outside the cell increases as pure water freezes, creating an osmotic gradient that pulls water outward. The cells shrivel and dehydrate, leading to osmotic collapse, which is just as deadly as the physical stabbing from ice crystals. So, even if you could thaw the body perfectly, the cells are already dead or dying from this double whammy of piercing and dehydration. This is why cryonics isn't as simple as popping someone into a freezer. It's a race against physics to prevent ice from forming in the first place. The kinetics of ice formation refer to how fast crystals grow, and thermodynamics deals with the energy changes involved. Understanding these principles is crucial because ice doesn't form instantly everywhere at once. It starts in specific areas where nucleation sites exist, like on cell membranes or within organelles, and then spreads. The rate of cooling plays a big role here. If you cool too slowly, large, jagged crystals have time to grow, causing extensive damage. If you cool too quickly, you might get smaller crystals, but they can still form in critical areas. This delicate balance is why researchers spend so much time studying the precise conditions under which ice forms in biological tissues. For astronauts in deep space, where temperatures can plummet, any failure in cryopreservation would mean certain death, as the damage is irreversible with current technology. The sharp edges of ice crystals are like microscopic knives, slicing through mitochondria, the powerhouses of cells, and disrupting the endoplasmic reticulum, which is vital for protein synthesis. Blood vessels aren't spared either. They can burst from the pressure of expanding ice, leading to internal bleeding that would be catastrophic upon thawing. Think of it as trying to preserve a complex network of pipes and wires by filling them with expanding ice. Everything gets torn apart from the inside. This isn't theoretical. Experiments on animal tissues have shown that frozen and thawed samples often resemble pulp rather than functional organs. The brain, being particularly sensitive, would suffer immense damage, with ice crystals likely destroying neural connections that store memories and personality. That's a far cry from the sci-fi trope of waking up unchanged after centuries. Another aspect often overlooked is that different tissues have different water contents, so they freeze at varying rates. For example, muscles with high water content freeze faster than fatty tissues, leading to uneven stress and potential cracking between organs. This lack of uniformity means that even if one part of the body is somewhat preserved, others are utterly destroyed. Moreover, the formation of ice isn't just a surface issue. It happens deep within tissues, where it's harder to control. In space, where gravity is minimal, fluid distribution could be uneven, potentially creating pockets where ice forms more readily, exacerbating the problem. So, how do scientists tackle this? The first step is to understand the enemy, which is why cryobiology focuses heavily on the physics of ice nucleation and growth, by studying how ice forms in different cellular environments. Researchers can develop methods to interfere with the process. One approach is to use chemicals that lower the freezing point of water. But that's not enough to prevent crystallization entirely. Instead, the goal is to achieve vitrification, where tissues turn into a glass-like solid without ice crystals. But that's a topic for another discussion. For now, it's key to recognize that ice formation is the primary hurdle. The irony is profound. Water, which is essential for every biochemical reaction in our bodies, becomes the agent of destruction during freezing. This transformation from life-giver to executioner is a central paradox in cryonics. In everyday life, we see examples of this damage when frozen fruits thaw into mushy, watery messes, or when frostbitten tissues die and slough off. Our bodies aren't designed to handle such extremes. Evolution has optimized us for a narrow temperature range. When we push beyond that, chaos ensues at the cellular level. For long-duration space missions, finding a way to prevent ice formation is non-negotiable. Without a solution, astronauts would be permanently damaged before they even reach their destination. Current research involves using cryoprotectants, which are substances that help prevent ice formation, but they come with their own challenges, like toxicity, which we'll explore later. But even with cryoprotectants, completely avoiding ice crystals in large organisms like humans is incredibly difficult. The process requires precise control over cooling rates and the distribution of these chemicals throughout the body. In small samples, like individual cells or tiny tissues, it's more manageable, but scaling up to a whole human is a monumental task. This is why cryonics for space travel remains in the experimental phase. The damage from ice crystals isn't just about immediate cell death. It also triggers inflammatory responses and other secondary effects that would complicate any attempt at reanimation. For instance, when cells rupture, they release their contents into the surrounding tissue, which can cause immune reactions and further damage. In a frozen state, these processes are halted, but upon thawing, they would kick in, leading to rapid deterioration. So, even if you could somehow repair the physical holes, the biochemical chaos would still be a major issue. This underscores the importance of preventing ice formation entirely rather than trying to fix the damage afterward. In summary, the formation of lethal ice crystals is the internal enemy that must be defeated for cryonics to have any chance of success. It's a complex problem rooted in basic physics and biology, and it requires a deep understanding of how water behaves under extreme conditions. For astronauts dreaming of travelling to distant stars, overcoming this obstacle is the first critical step. Without it, the journey would be futile, as the body would not survive the process. So, as we continue to explore the cosmos, we must also delve into the microscopic world of ice crystals, where the battle for preservation is fought one cell at a time. This isn't just about technology. It's about rethinking our approach to life itself in the harsh environment of space. By focusing on this fundamental issue, we can develop better strategies for long-term survival beyond Earth. The dream of suspended animation depends on it, and every breakthrough in understanding ice formation brings us closer to making that dream a reality. But for now, the enemy within remains a formidable foe, reminding us of the delicate balance between life and the cold void of space. So, if ice crystals are the destructive enemy within that shatter our cells during freezing, then the scientific workaround, DOT, known as vitrification, is the clever trick that aims to freeze the body without actually letting ice form at all. Think of it as trying to solidify a liquid into something like glass instead of into a crystalline, jagged structure. This process involves cooling the body down to incredibly low temperatures, similar to those used in traditional cryonics, but with a crucial twist. The tissues are permeated with high concentrations of special chemicals called cryoprotectants before cooling begins. These cryoprotectants act as a biological antifreeze, disrupting the natural tendency of water molecules to arrange themselves into ice crystals. Instead, as the temperature drops, the entire solution inside and around the cells becomes so viscous that it hardens into a stable, amorphous solid, much like how molten glass cools into a window pane. This glassy state preserves the intricate architecture of cells, organelles, and blood vessels without the piercing damage caused by ice, offering a glimpse of hope for long-term preservation. The key to vitrification lies in the precise chemistry of these cryoprotectant solutions. They are typically compounds like glycerol, dimethyl sulfoxide, or ethylene glycol, which work by binding to water molecules and interfering with the hydrogen bonding that leads to crystal formation. When perfused throughout the body, they effectively lower the freezing point of the cellular environment and increase the viscosity, so that during rapid cooling, the water molecules simply don't have the time or space to organize into ice. Instead, the entire system undergoes a phase transition directly from a liquid to a solid without passing through the crystalline phase. Hence the term vitrification from the Latin word for glass. This isn't just a theoretical concept. It has been successfully applied in medical fields like fertility preservation, where eggs and embryos are vitrified for in vitro fertilization, allowing them to be stored indefinitely and thawed with high survival rates. However, scaling this up from tiny clusters of cells to an entire human body is where the challenges become monumental. For astronauts, the goal would be to vitrify the entire organism, but the human body is vastly more complex than a few milliliters of reproductive cells. One major hurdle is achieving uniform perfusion of cryoprotectants throughout all tissues. The circulatory system must be thoroughly flushed with these chemicals to ensure every cell, from the brain's neurons to the skin's fibroblasts, is protected. But different organs have varying densities, blood flow rates, and cellular compositions, which can lead to uneven distribution. For instance, the brain, protected by the blood-brain barrier, might resist full saturation, leaving neurons vulnerable to ice formation. Moreover, the high concentrations of cryoprotectants required for effective vitrification are themselves toxic to cells. These chemicals can cause osmotic shock during the perfusion process, where water rapidly leaves cells to balance the solute concentration, leading to shrinkage and damage before freezing even begins. Even if perfusion is successful, the cooling rate must be meticulously controlled. Too slow, and ice might still form in some areas. Too fast, and thermal stress could cause fracturing in the vitrified tissue. Once vitrified, the body would be maintained at temperatures around -196 degrees Celsius, typically using liquid nitrogen, where all biological activity is effectively paused. But the process doesn't end there. Rewarming is equally critical and fraught with its own dangers, which we'll touch on later. For now, vitrification represents the most promising path toward viable suspended animation because it addresses the core issue of ice damage head-on. In experiments with small animals and organs, vitrification has shown remarkable results. For example, researchers have successfully vitrified and revived small sections of brain tissue from rodents, with synaptic structures appearing intact under electron microscopy. This is a huge step forward, as it suggests that the complex wiring of the brain, which stores memories and personality, might be preserved. However, for a full-sized human, the technical barriers are staggering. The volume of cryoprotectant needed is enormous, and ensuring it reaches every capillary in the body without causing toxicity or ischemia is a bioengineering nightmare. Additionally, the cooling equipment must be sophisticated enough to handle the thermal mass of a human without introducing gradients that lead to cracking. In space, these challenges are compounded by microgravity, which could affect how cryoprotectants perfuse through the circulatory system. On Earth, gravity aids in fluid distribution, but in zero-G, fluids behave differently, potentially pooling in certain areas and leaving others dry. This could create pockets where ice crystals form, undermining the entire process. Furthermore, the spacecraft itself would need to house advanced life support systems that can initiate vitrification rapidly after clinical death, as any delay could lead to ischemic damage from oxygen deprivation. The capsule would have to be more than a freezer. It would be a medical device capable of automated perfusion, cooling, and monitoring over centuries. Despite these hurdles, vitrification is actively being researched for organ transplantation. Scientists are working on vitrifying kidneys, livers, and hearts to extend their storage time beyond the few hours currently possible with ice-based preservation. Success in this area could pave the way for whole-body applications, but it's a gradual process. Each organ presents unique challenges. For instance, the heart's muscle cells have different metabolic needs than the liver's hepatocytes, requiring tailored cryoprotectant cocktails for astronauts on interstellar missions. Vitrification could theoretically allow them to travel for centuries without aging, arriving at distant star systems ready to be revived. But this relies on future advancements in rewarming techniques and medical technology that may not yet exist. The vitrified state is metastable, meaning that over very long periods, even in deep cold, the glassy material could devitrify and form ice crystals spontaneously due to background radiation or quantum effects. Thus, the capsule must also shield against cosmic rays to prevent cumulative damage. In summary, vitrification is a brilliant workaround to the ice crystal problem, leveraging biochemistry to cheat physics and preserve life in a state of suspended animation. It's not the simple freeze of science fiction, but a complex, delicate procedure that turns the body into a biological glass sculpture. For space exploration, mastering vitrification could be the key to unlocking the stars, but it requires solving issues of toxicity, perfusion, cooling uniformity, and long-term stability. As research progresses, Each small success in vitrifying larger tissues brings us closer to that goal. But for now, it remains a promising yet unproven technology for human space travel. The dream of freezing without freezing is within reach scientifically, but practically, it's a steep climb that will demand innovation across multiple disciplines. But while vitrification offers a way to bypass the destructive power of ice crystals, it introduces a new and equally formidable challenge. The very chemicals that make it possible are poisonous to the cells they are meant to protect. These cryoprotectants, essential for preventing ice formation, are themselves highly toxic compounds that can cause severe damage or death to cells if not managed with extreme precision. The entire endeavour of vitrification becomes a delicate balancing act, a high-stakes trade-off where scientists must navigate between the Scylla of ice crystal formation and the Charybdis of chemical poisoning. The primary issue is that the concentrations of cryoprotectants required to achieve successful vitrification in something as large as a human body are immense, and at these levels, the chemicals can disrupt cellular functions in multiple ways. For instance, they can interfere with enzyme activity, denature proteins, and disrupt the lipid bilayers of cell membranes, essentially causing cells to fall apart from the inside. Moreover, the process of introducing these chemicals into the body is fraught with peril, as the cryoprotectant solution is perfused through the circulatory system. It creates an osmotic shock. Cells are suddenly exposed to an environment with a much higher solute concentration outside than inside, which causes water to rush out of the cells rapidly to balance the osmotic pressure. This leads to cellular dehydration and shrinkage, which can be so severe that it damages the cell's structure irreparably before the cooling even begins. Then, if the cells survive the initial perfusion, they must endure the prolonged exposure to these toxic chemicals during the cooling phase and the subsequent storage at cryogenic temperatures. Even in a vitrified state, some low-level chemical reactions might still occur over centuries, potentially leading to cumulative damage. The challenge is further complicated by the fact that different types of cells and tissues have wildly varying tolerances to these cryoprotectants. For example, neurons in the brain are exceptionally sensitive to chemical insults, while muscle cells might withstand higher concentrations, but not without risk. This variability means that a protocol that perfectly preserves the liver might utterly destroy the brain or the kidneys, making uniform protection of an entire organism a monumental puzzle. Researchers are therefore tasked with finding the Goldilocks zone for each tissue type, a concentration of cryoprotectant that is high enough to prevent ice formation during cooling and warming, but low enough to avoid triggering toxic responses or osmotic collapse. This is not a one-size-fits-all situation. It requires tailored approaches for different organs, which is incredibly difficult to achieve in a whole-body context. Current research focuses on developing what are often called smarter or less toxic cryoprotectants. These are new chemical formulations designed to be more biocompatible, perhaps by mimicking natural antifreeze proteins found in certain fish and insects, which protect them from freezing without causing harm. Another approach involves using cocktails of multiple cryoprotectants at lower individual concentrations, so that their combined effect prevents ice formation while minimizing the toxicity of any single compound. Additionally, scientists are refining the protocols for perfusion and washout, the process of removing cryoprotectants during rewarming. The goal is to create extremely controlled, step-by-step procedures that slowly introduce and remove the chemicals, giving cells time to adjust osmotically and reducing stress. For instance, instead of flooding the system all at once, a gradual perfusion with increasing concentrations might allow cells to acclimatize, similar to how a diver ascends slowly to avoid the bends. Similarly, during rewarming, A carefully managed washout process is critical to prevent a reverse osmotic shock, where water rushes back into cells too quickly, causing them to swell and burst. In the context of space travel for astronauts, these challenges are magnified. The perfusion equipment on a spacecraft would need to be fully automated and incredibly reliable, capable of executing these complex protocols without human intervention, as any error could be fatal. Furthermore, the microgravity environment of space could affect how cryoprotectants distribute through the body. Without gravity, fluids might not perfuse uniformly, leading to pockets where concentrations are too high, causing toxicity, or too low, allowing ice to form. This non-uniform perfusion could result in patchy preservation, where some parts of the body are perfectly vitrified while others are either poisoned or crystallized. The toxicity dilemma also has ethical implications. Subjecting astronauts to these procedures involves known risks of chemical poisoning based on current understanding, and the long-term effects are entirely unknown. It raises the question of whether it is justified to use a technology that might cause significant damage, even if it prevents another kind of damage. This trade-off forces scientists to constantly weigh the probability of ice-related destruction against the certainty of chemical harm at various concentrations. In laboratory settings, experiments on tissues and small organs have shown that optimizing these factors is possible on a small scale, but scaling up to a human remains a huge hurdle. For example, researchers have successfully vitrified and revived rodent ovaries or small brain slices, but doing the same for a whole human body is orders of magnitude more complex. The volume of cryoprotectant required is vast, and ensuring it reaches every single cell in a large, dense organ like the brain is a bioengineering nightmare. Moreover, the time factor is critical. The perfusion must be completed quickly after clinical death to minimize ischemic damage, but rushing it increases the risk of osmotic shock. This creates a tight window where every second counts, and the margin for error is virtually zero. In summary, the toxicity of cryoprotectants represents one of the most significant practical obstacles to making human cryonics viable for space travel. It transforms the problem from a purely physical one of preventing ice to a biochemical one of managing poison. While vitrification is the most promising technique we have, its success hinges on our ability to mitigate the very real dangers posed by the protective chemicals themselves. Ongoing research into less toxic agents and better perfusion protocols offers hope, but for now, this remains a major bottleneck. The dream of suspending astronauts for long journeys depends on solving this chemical puzzle, ensuring that the remedy for freezing does not become the cause of death. As we push the boundaries of cryobiology, each discovery in reducing toxicity brings us a step closer. But the path is long and fraught with challenges that require innovative solutions and a deep understanding of cellular physiology. So, having navigated the treacherous waters of cryoprotectant toxicity, where the very chemicals meant to save the cells could poison them, we arrive at what many scientists consider the most precarious part of the entire cryonics process: rewarming. It is a phase so critical that a single misstep can undo all the painstaking work of vitrification, turning a perfectly preserved glassy body into a shattered, icy ruin. Imagine going through the immense effort of perfectly vitrifying an astronaut, only to have them destroyed not by the cold, but by the heat applied to bring them back. This is because the vitrified state is metastable. It's not a permanent condition, but a delicate one that can easily collapse back into the destructive ice crystals we worked so hard to avoid if rewarming is not executed with absolute precision. The primary danger during rewarming is a phenomenon called devitrification, If the temperature rises too slowly, the molecules within the vitrified solution gain just enough energy to start moving and reorganizing themselves into crystalline structures, ice, effectively nullifying the entire preservation effort. It is like carefully avoiding a trap during the freeze, only to stumble right into it during the thaw. But speed alone is not the answer. Rewarming must also be perfectly uniform throughout the entire volume of the body. If some parts heat up faster than others, the resulting temperature gradients create immense mechanical stresses. Think of a glass jar taken from the freezer and plunged into hot water. It cracks due to the uneven expansion. Now, scale that up to a human body, where the difference in thermal expansion between the warmer surface and the colder core can literally cause tissues and organs to fracture. These cracks are not just superficial. They can sever blood vessels, disrupt neural pathways, and rend organs apart, making reanimation impossible. This makes safe rewarming a colossal thermal engineering challenge, one that requires heating the body from the inside out to ensure homogeneity. One of the most promising techniques being investigated for this is nanowarming, or nanoparticle heating. This involves injecting tiny magnetic nanoparticles throughout the body before vitrification. During rewarming, the body is exposed to an alternating magnetic field, which causes these nanoparticles to vibrate and generate heat uniformly from within. This internal heating aims to warm the entire body simultaneously, minimizing temperature gradients and reducing the risk of thermal stress and cracking. Another approach involves using infrared radiation or carefully controlled microwave energy. But these methods struggle with penetration depth and can cause hotspots if not perfectly calibrated. The key is to achieve a rewarming rate that is fast enough to bypass devitrification, often requiring rates of hundreds of degrees per minute while maintaining perfect temperature uniformity across all tissues. For a small sample, like a tiny cluster of cells or a small organ, this is challenging but feasible in lab settings. However, scaling this up to a whole human is an entirely different matter. The human body is a large, thermally massive object with varying densities and thermal conductivities in different tissues. Bone, for instance, heats differently from muscle, and fat insulates differently from blood-rich organs. This heterogeneity means that even with advanced techniques like nanoparticle heating, ensuring that every cubic millimetre of the body warms at exactly the same rate is a monumental task. Any area that lags behind risks devitrifying, while any area that gets too hot risks thermal damage or even cooking the tissues. Moreover, the nanoparticles themselves must be distributed perfectly uniformly during the initial perfusion, which is another logistical nightmare given the complexity of the human circulatory system. If some capillaries are blocked or if flow is uneven, certain regions might receive no nanoparticles, leading to cold spots where ice can form. Additionally, the long-term effects of having these nanoparticles embedded in the body are unknown. They could cause toxicity or interfere with cellular function upon revival. In the context of space travel, these challenges are exacerbated. The rewarming equipment on a spacecraft must be fully automated and incredibly reliable, capable of operating flawlessly after centuries of dormancy. It must also function in microgravity, where fluid dynamics are different, potentially affecting how heat distributes through tissues. Without gravity, convection currents are absent, which could lead to stagnant zones that heat unevenly. The capsule would need sophisticated sensors to monitor temperature in real time throughout the body and adjust the heating parameters dynamically to correct for any inhomogeneities. This requires a level of artificial intelligence and robotics that is currently beyond our reach. Furthermore, the rewarming process must be seamlessly integrated with the washout of cryoprotectants. As the body warms, The toxic cryoprotectants need to be flushed out and replaced with a biocompatible solution like blood or a synthetic substitute. This must happen quickly to prevent chemical damage as temperatures rise, but also carefully to avoid osmotic shock. If the washout is too rapid, cells might swell and burst from the influx of water. If too slow, the lingering cryoprotectants could become toxic at higher temperatures. This adds another layer of complexity to an already fraught process. Even if we overcome these technical hurdles, there is the biological aspect. Cells that have been in metabolic arrest for centuries need to restart their functions simultaneously. Mitochondria must begin producing energy, ion channels must reopen, and enzymatic processes must resume in a coordinated fashion. If rewarming is not perfect, some cells might revive while others die, leading to a cascade of failure. For instance, if neurons in the brain do not all revive at the same time, it could result in seizures, coma, or irreversible brain damage. The heart must be warmed evenly to avoid arrhythmias, and the lungs must be ready to oxygenate blood immediately. This is why rewarming is not just a physical heating process, but a biological resuscitation event that demands precision across multiple disciplines. Current research is focused on improving rewarming techniques through computational modeling and experimental trials. Scientists use simulations to predict heat flow in virtual human bodies, testing different heating methods and protocols to identify potential pitfalls. In the lab, they are experimenting with larger tissue samples and small organs, gradually scaling up the technology. For example, there have been successes in vitrifying and rewarming rabbit kidneys with some function restored, but these are still far from human-scale applications. Each small advance brings hope, but the path to safely rewarming a whole human remains long and uncertain. In summary, the challenge of rewarming is the final and perhaps most dramatic obstacle in the cryonics journey for astronauts. It is a phase where the margin for error is virtually zero, and the consequences of failure are absolute. While vitrification allows us to preserve the body without ice damage, rewarming is the gatekeeper to revival, demanding a solution that is both rapid and perfectly uniform. Without a reliable rewarming method, all previous steps are futile, and the dream of suspended animation remains out of reach. As we continue to explore the cosmos, solving this thermal puzzle is essential, requiring innovations in engineering, biology, and materials science to ensure that when astronauts are warmed from their frozen slumber, they awaken intact and healthy, ready to step onto new worlds. But even if we miraculously solve the immense challenges of rewarming and successfully revive a physically intact body, we face an even more profound question. Would the person who wakes up still be the same astronaut who embarked on the journey? Or would they be a blank slate, a stranger in their own mind? This brings us to the absolute core of cryonics for human space travel, the preservation of neural connectivity. It is not enough to simply keep cells alive. We must preserve the intricate, delicate wiring of the brain that encodes every memory, every skill, every emotion, and every facet of personality that makes a person who they are. This complex network of connections between neurons, known as the connectome, is the biological substrate of the self. Think of it not as a static blueprint, but as a dynamic, living circuit board that is constantly being modified by experience. For an astronaut to retain their identity after centuries in stasis, cryopreservation must safeguard this synaptic information at a molecular level. Any damage, no matter how microscopic, to this network could result in the loss of specific memories, subtle alterations in character, or in the worst case, a complete failure to regain consciousness. leaving a technically alive but mentally void body. The primary challenge is that the brain is not a homogeneous organ. It is an incredibly dense and complex tapestry of billions of neurons, each connected to thousands of others through synapses. These synapses are not just simple connections. They are sophisticated structures involving vesicles filled with neurotransmitters, receptors, and a scaffold of proteins that can change in strength and number based on neural activity. This synaptic plasticity is the very basis of learning and memory. The fear is that the process of vitrification, while preventing gross ice crystal damage, might still cause subtle shifts or disruptions at this ultrastructural level. The high concentrations of cryoprotectants needed could cross-link proteins or alter the lipid membranes of synaptic vesicles, potentially scrambling the information they hold. Similarly, the mechanical stresses from cooling and rewarming, even if they don't cause visible cracks, could distort the precise geometry of dendritic spines or axonal terminals where synapses reside. We simply do not know yet if current vitrification techniques are sufficiently refined to preserve these patterns with the fidelity required for functional recovery. Research on small pieces of brain tissue, like hippocampal slices from rodents, has shown that vitrification can preserve overall cellular structure and even some electrical activity after rewarming. But whether it preserves the exact synaptic weights and connectivity that encode a lifetime of experiences is still an open question. It is one thing to keep neurons alive. It is entirely another to keep the pattern of their connections perfectly intact. This is the gold standard for any successful cryonic mission: the integrity of the connectome. Without it, the revived astronaut might have a working body but a corrupted operating system. They could suffer from amnesia, unable to recall their training, their mission objectives, or their loved ones. Their personality could be altered, their decision-making impaired, or their emotional responses muted. In essence, the person who was sent on the mission would be gone, replaced by a similar but fundamentally different individual. This raises a stark scientific and ethical dilemma. Is the physical structure of the brain alone sufficient to reconstitute consciousness and identity? We currently operate on the assumption that it is, that all mental processes arise from biological functions. But if the structure is damaged, even minutely, can we ever truly get the original person back? This is not just a philosophical pondering. It has direct practical implications for how we design cryonic protocols. The brain is particularly vulnerable because it has a high metabolic rate and is exquisitely sensitive to oxygen deprivation, toxic insults, and physical trauma. The minutes between clinical death and the initiation of cryopreservation, known as the ischemic period, can cause significant damage to neural tissues even before cooling begins. Therefore, for space missions, the capsule would need integrated systems to begin perfusion and cooling almost instantaneously after vital signs stop, a logistical nightmare in itself. Furthermore, the blood-brain barrier, which protects the brain from many circulating substances, can also hinder the uniform distribution of cryoprotectants, potentially leaving some neural regions unprotected and prone to ice formation or toxicity. Ensuring that the cryoprotectant solution reaches every single synapse in the brain is a perfusion challenge of the highest order. Current methods of verifying connectome preservation are also destructive. To map a connectome with today's technology, the brain tissue must be sliced into incredibly thin sections and imaged under an electron microscope, a process that obviously kills the tissue. We lack a non-invasive way to scan a living, vitrified brain and confirm that all its synaptic connections are perfectly preserved. This means we would not know if the preservation was successful until after rewarming and revival, which is far too late. Some researchers speculate that future nanotechnology could potentially repair any synaptic damage, scanning the original structure and making corrections. But this is purely speculative and relies on technologies that do not yet exist. For a practical mission, we cannot bank on such future miracles. We need to achieve preservation with the tools and understanding we have or can realistically develop. The focus, then, must be on refining vitrification protocols specifically for neural tissue. This involves optimizing cryoprotectant cocktails for the brain, developing faster and more uniform cooling and rewarming methods to minimize mechanical stress, and finding ways to mitigate ischemic damage before preservation begins. Experiments are ongoing with increasingly complex neural systems, from simple worm connectomies to larger mammalian brain tissues, to test the limits of what can be preserved and recovered. Each small success is a step forward, but the leap to a whole human brain is enormous. In the context of space, the added factors of microgravity and cosmic radiation could further complicate neural preservation. Radiation, in particular, poses a long-term threat, as it can cause cumulative DNA damage and other molecular changes even at cryogenic temperatures, potentially degrading the connectome over centuries of travel. The capsule would need to be a superb radiation shield as well as a cryogenic chamber. Ultimately, the preservation of neural connectivity is the non-negotiable linchpin of interstellar cryonics. All the other challenges, preventing ice, managing toxicity, achieving perfect rewarming, are ultimately in service of this single goal, keeping the astronaut's mind intact. If we cannot guarantee the safety of the connectome, then the entire mission is pointless, as the person who arrives at the destination would not be the person who left. It is the ultimate engineering and biological challenge, demanding a depth of understanding about the brain that we are only beginning to scratch the surface of. As we push the boundaries of cryobiology and neuroscience, the quest to preserve the self drives innovation, but it also humbles us with the sheer complexity of what we are trying to achieve. For now, the key to you remains locked within the delicate, frozen web of neural connections, waiting for science to find a way to keep it safe across the vast, cold expanse of space. So, after grappling with the immense complexity of preserving the brain's delicate neural connections, we now have to zoom out and confront an even broader challenge: the stark difference between preserving a single organ and preserving an entire, integrated human body. It is significantly easier to vitrify and reanimate a single organ, like a kidney or a heart, than it is to deal with a complete multicellular organism. This isn't just a matter of size. It's about the profound complexity that arises from the interaction of countless different tissue types, each with its own unique biological properties. Think of it like this. Preserving a single organ is a difficult but manageable engineering problem, while preserving a whole body is like trying to coordinate an entire city's infrastructure to function in perfect harmony during a deep freeze and then reboot without a single error. The reason for this disparity lies in the fundamental heterogeneity of the human body. Different organs have vastly different metabolic rates, cellular densities, and water compositions, which means they respond to cooling and warming at dramatically different rates. For instance, the liver is a metabolically active organ with a high water content, so it might freeze and thaw relatively quickly, while bones, being denser and less hydrated, would respond much more slowly. This lack of uniformity isn't just a minor inconvenience. It can cause catastrophic mechanical and functional stresses during both the cooling and the rewarming phases. When you cool the body, these different thermal expansion coefficients mean that some tissues contract faster than others, creating shear forces that can tear connections between organs and damage delicate blood vessels. during rewarming. The same issue arises in reverse. If one organ heats up and expands faster than its neighbouring tissue, it can cause cracking or ripping at the interfaces. This is why a cryopreservation protocol that works perfectly for the liver might be utterly fatal for the brain or the skin. The brain, as we've discussed, is exquisitely sensitive to any disruption, while the skin might be more resilient but still has its own specific requirements. Developing a single technique that can protect all organ systems simultaneously and harmoniously is one of the greatest scaling challenges in cryobiology. The leap from preserving individual organs to preserving the whole body is as monumental as the leap was from preserving individual cells to preserving an entire organ. When scientists work on organ preservation, they can tailor the cryoprotectant solution and the cooling rate specifically for that organ's cellular structure and function. For example, doctor protocols for preserving kidneys for transplantation are quite advanced and can keep the organ viable for several hours. But these are not directly applicable to a whole body. In a whole body, you have to find a compromise. A one-size-fits-all solution that somehow works for every single tissue type, from the fatty deposits in adipose tissue to the neural networks in the brain. And this is incredibly difficult. The circulatory system itself adds another layer of complexity. To perfuse cryoprotectants uniformly throughout the entire body, the solution must travel through miles of blood vessels, from large arteries down to tiny capillaries, and ensure that every cell receives the correct concentration. But blood flow isn't perfectly uniform. There are variations in pressure and flow rates in different parts of the body. Organs like the brain have a protective blood-brain barrier that can resist the penetration of certain cryoprotectants, while other areas might be more permeable. This can lead to uneven protection, where some organs are perfectly vitrified while others are either underprotected and form ice or oversaturated and suffer from toxicity. Moreover, the process of cooling a whole body is not instantaneous. Heat transfer takes time, and the outer layers of the body will cool faster than the core. This temperature gradient can cause the outer tissues to vitrify while the core is still warm enough for ice crystals to form, or vice versa during rewarming. This is why techniques like nanoparticle heating are being explored for whole body rewarming, to try and heat the body from the inside out. But even that is not a guaranteed solution for achieving perfect uniformity across all organs. Another critical issue is the functional integration of organs. The human body is not a collection of independent parts. It's an interconnected system where organs communicate and depend on each other. The liver detoxifies the blood, the kidneys filter it, the heart pumps it, and the brain regulates everything. If one organ is damaged during cryopreservation, it could lead to a cascade of failure upon revival. For instance, if the heart is revived but the kidneys are not, the body would quickly succumb to toxin buildup. Or if the brain is preserved but the endocrine system is compromised, hormonal imbalances could prevent proper function. This interdependence means that success is all or nothing. Every major organ system must be revived in a functional state for the astronaut to survive. In space, these challenges are magnified by the environment. Microgravity could affect how cryoprotectants perfuse through the body, potentially leading to fluid pooling and uneven distribution. The long-term stability of the vitrified state across different organs is also unknown. Some tissues might be more prone to devitrification over centuries than others. Furthermore, the capsule must be designed to maintain a stable temperature for all organs simultaneously, which requires sophisticated thermal management systems that can account for the different thermal masses and properties of each organ. The economic and practical implications are also significant. Research into organ cryopreservation has tangible benefits for medicine today, such as extending the storage time of organs for transplantation, which saves lives. This research provides a stepping stone towards whole-body preservation, but the funding and effort required to scale up to a human are astronomical. It involves not just biological research, but also advances in materials science, engineering, and computational modelling to simulate heat transfer and stress distribution throughout the body. In conclusion, the differential freezing of organs versus the whole organism represents a fundamental barrier in making cryonics viable for space travel. While we are making progress with individual organs, the jump to a complete human body is enormous and requires a holistic approach that considers the body as an integrated system. For astronauts, this means that we cannot simply apply organ-based protocols to the whole body. We need to develop entirely new strategies that ensure uniform protection and revival of all tissues. Until we can solve this scaling problem, the dream of suspending astronauts for long journeys will remain just that, a dream. The path forward involves continued research in organ preservation, coupled with efforts to understand and mitigate the stresses that arise when scaling up to the whole body. It's a daunting task, but each small breakthrough brings us closer to understanding how to protect a human being in its entirety, not just in parts. But even if we could somehow solve the monumental puzzle of uniformly preserving and reviving an entire human body on Earth, we must now confront the brutal reality that space is not a benign, empty void. It is an actively hostile environment that adds layers of complexity we are only beginning to understand. The challenges of microgravity and cosmic radiation fundamentally alter the game for cryonics, introducing problems that simply do not exist in terrestrial labs. Let's start with microgravity. On Earth, gravity plays a crucial role in how fluids behave within our bodies. Our circulatory system relies on gravity to some extent to help distribute blood, with pumps like the heart working against a consistent downward pull. In the microgravity of space, fluids redistribute evenly, causing what astronauts often call puffy head syndrome, where fluids shift towards the upper body and head. Now, imagine trying to perfuse a viscous cryoprotectant solution through this system. The uniform distribution of these chemicals, which is difficult enough on Earth, becomes a nightmare in zero-G, without gravity to assist. Cryoprotectants might not perfuse evenly through the entire circulatory network. They could pool in certain areas, leaving other regions underprotected and vulnerable to ice formation during cooling. Conversely, some areas might receive an overdose, leading to localized toxicity that kills cells before the freeze even begins. This uneven perfusion could create microscopic pockets where ice crystals form undetected, sabotaging the entire vitrification process from within. Furthermore, the lack of gravity means that convection currents, which help mix and distribute heat and fluids on Earth, are absent. This could lead to stagnant zones in tissues where temperature control during cooling or rewarming is imperfect, increasing the risk of devitrification or thermal cracking. Now, let's talk about the even more insidious threat: cosmic radiation. Deep space is flooded with high-energy particles from cosmic rays, gamma rays, DOT, and solar flares. Here on Earth, we are protected by our planet's magnetic field and atmosphere, but outside this bubble, astronauts are exposed to a constant, silent barrage of radiation. This radiation is powerful enough to smash through DNA strands, causing breaks and mutations even at normal, living temperatures. The real question for long-duration cryonic travel is what this radiation does to a body preserved at cryogenic temperatures over centuries. We simply do not know. While metabolic activity is paused, the physical interaction between high-energy particles and biological molecules is not. DNA, proteins, and lipids can still be damaged by ionizing radiation. Over hundreds or thousands of years, this damage could accumulate, leading to a slow, steady degradation of the vitrified tissues. Imagine the genetic code in every cell gradually being chipped away, with mutations piling up. Upon revival, this could mean a high risk of cancers, cellular dysfunction, or even the failure of critical systems to reboot properly. The brain's connectome, which we discussed as the seat of identity, could be particularly vulnerable. Radiation-induced damage to the delicate synaptic structures or to the DNA within neurons could corrupt the very data we are trying to preserve, leading to memory loss or cognitive decline after reanimation. This is a largely unexplored field of research because we have never attempted to preserve biological material in space for such long periods. The capsule designed to carry these astronauts, therefore, cannot be a simple freezer. It must be an ultra-advanced cryogenic and radiological shield. It needs to maintain a stable temperature of around -196 degrees Celsius for millennia, while also protecting its fragile cargo from a relentless hailstorm of atomic nuclei travelling at nearly the speed of light. Building such a shield is an engineering challenge of epic proportions. Lead shielding is too heavy, and lighter materials might not be effective enough. We might need active shielding, like magnetic fields, similar to a miniature version of Earth's magnetosphere. But generating and maintaining such fields over centuries with perfect reliability is currently science fiction. The capsule must also be resilient enough to withstand impacts from micrometeoroids, which are tiny but travel at incredible speeds and could puncture the shield, compromising both temperature and radiation protection. Moreover, the capsule's systems must be fail-safe. There is no possibility for maintenance or repairs during the journey. A single power failure, a tiny leak, or a component degradation over time could mean the difference between a successful mission and a tomb drifting endlessly in the void. The interaction between the physics of cryopreservation and the harsh conditions of deep space creates a problem set that we are only starting to grapple with. For instance, how does radiation affect the vitrified state itself? Could it cause the glassy matrix to become brittle or promote devitrification over time? These are unanswered questions. Furthermore, the combined effects of microgravity during the initial perfusion and radiation during storage mean that the protocols developed on Earth might be wholly inadequate for space applications. We cannot simply test cryonics in a lab on Earth and assume it will work the same way on a centuries-long journey to another star. The space environment forces us to rethink every assumption. It adds variables that are difficult to simulate and even harder to mitigate. For astronauts undergoing cryonic preservation, the mission doesn't end when they are frozen. The capsule becomes their entire world, and its ability to defend against the silent, invisible threats of space will determine their ultimate fate. This underscores the need for interdisciplinary research that brings together cryobiologists, radiation experts, and aerospace engineers. We need to run experiments on the International Space Station or future lunar gateways to see how cryoprotectants perfuse in microgravity and how radiation affects vitrified tissues over time. Until we have that data, cryonics for space travel remains a speculative dream, vulnerable to the very real and active dangers that lie between the stars. The void of space is not empty. It is a dynamic and destructive environment that will test the limits of our technology and our understanding of biology in ways we are only beginning to imagine. Given the relentless threats of cosmic radiation and the peculiarities of microgravity, the only thing standing between a perfectly preserved astronaut and certain destruction is the cryogenic capsule itself, a piece of engineering that must be infinitely more sophisticated than a simple freezer. This capsule is not a passive storage container. It is a high-technology, passive life support system designed to maintain an unbelievably stable temperature of around -196 degrees Celsius for centuries, possibly even millennia, without fail. Imagine the reliability required for a machine to operate flawlessly for a duration longer than most civilizations have existed, with no opportunity for repairs or maintenance once the journey begins. The engineering challenges begin with thermal management. Maintaining such an extreme low temperature in the vacuum of space, where heat can only be lost through radiation, requires a perfectly insulated system. But it is not just about keeping the cold in. It is also about managing any external heat sources, like the occasional pass near a star or internal heat from any electronic systems that must remain active for monitoring. The capsule must have redundant cooling systems, likely using liquid nitrogen or even more advanced cryocoolers, with multiple independent power sources to prevent a single point of failure. A power outage lasting just a few days could be catastrophic, as the temperature would rise, leading to devitrification and the formation of those lethal ice crystals we've worked so hard to avoid. Beyond temperature, the capsule must be armoured against physical impacts. The space between stars is not empty. It is filled with micrometeoroids, tiny particles travelling at speeds of many kilometres per second. An impact from even a grain of sand-sized object could puncture the outer hull, compromising the vacuum insulation or damaging internal components. Therefore, the capsule needs a Whipple shield or similar multi-layered defense system that vaporizes incoming particles before they can cause serious damage. This shielding must be lightweight to avoid making the spacecraft too massive, yet strong enough to withstand countless potential impacts over centuries. Furthermore, the materials used in the capsule's construction must resist degradation over time. Metals can undergo embrittlement at cryogenic temperatures, and plastics or composites might outgas or become brittle after prolonged exposure to radiation and cold. Engineers must select materials that remain stable for unimaginable timescales, which means testing them in accelerated aging experiments that simulate millennia of wear and tear. Another critical aspect is the structural integrity during acceleration and deceleration. The capsule must withstand the forces of launch from Earth and then any course corrections or braking maneuvers at the destination, all while keeping its fragile, glass-like contents from experiencing vibrations or G-forces that could cause cracking. This requires sophisticated suspension systems inside the capsule to isolate the preserved bodies from any shocks. The capsule also needs to be a formidable radiation shield. As discussed, cosmic rays are a constant threat, and while the vitrified state might slow down some damage, it does not stop it entirely. The capsule must incorporate radiation shielding, which could be passive, using layers of hydrogen-rich materials like polyethylene or water, or active, involving magnetic fields to deflect charged particles. Active shielding would require power and incredibly reliable superconducting magnets, adding another layer of complexity and potential failure points. Power generation for such a long mission is another nightmare. Solar panels are useless far from stars, and nuclear batteries like RTGs have limited lifespans and might not provide enough energy for centuries. Perhaps the capsule would rely on stored energy or be part of a larger spacecraft with a robust nuclear reactor. But that introduces more systems that must remain functional. The monitoring systems within the capsule are equally vital. Sensors must continuously track internal temperature, pressure, radiation levels, and structural integrity. This data needs to be stored and possibly transmitted back to Earth or to the destination, requiring communication systems that also last for centuries. All this electronics must be hardened against radiation and designed for ultra-low power consumption to avoid generating excess heat. The software running these systems must be bug-free and capable of autonomous decision-making, as there will be no human intervention for hundreds of years. It must be able to detect anomalies, switch to backup systems, and perform repairs if possible, all without ever crashing or corrupting its memory. The sheer reliability required is unprecedented in human engineering. We have never built anything that must work perfectly for so long. Consider the Voyager probes, which have lasted for decades, but they are simple compared to a life support system for preserved humans. And even they have experienced component failures. The capsule is essentially a time capsule, but one that carries the ultimate precious cargo, human lives suspended in time. Its design is a challenge in materials science, thermodynamics, systems engineering, and reliability theory all rolled into one. Every weld, every circuit, every line of code must be perfect, and every possible failure mode must be anticipated and mitigated. For the astronauts inside, this capsule is everything. It is their tomb if the technology fails, or their cradle if it succeeds. The engineering effort to create such a vessel would be one of the most ambitious projects ever undertaken, requiring global collaboration and a commitment to a goal whose payoff would not be seen for generations. It forces us to think in timescales that are foreign to our everyday experience, planning for a future that is almost abstract in its distance. Yet, without this engineering marvel, all the advances in cryobiology would be meaningless, as the body would not survive the journey. The capsule is the silent guardian, the unblinking sentinel that must endure the utter silence and isolation of interstellar space, protecting its charge against all odds until the day. Hopefully, technology at the destination is advanced enough to bring its passengers back to life. This is not just a freezer. It is a testament to human ingenuity and our relentless drive to reach beyond our own world, even if we ourselves may not see the fruits of our labour. But even if we succeed in building that perfect, millennia-enduring capsule and flawlessly preserve the astronauts within it, we are then confronted with a profound and unsettling temporal paradox that strikes at the very purpose of the mission. Imagine the capsule finally arriving at its destination after a journey of several hundred years, its sophisticated systems having performed flawlessly, the bodies inside perfectly vitrified and untouched by ice or radiation. The preservation technology has worked, but now what? The society and technology that receive this time capsule from the past are likely to be utterly unrecognizable, having evolved in ways we cannot possibly predict from our current vantage point. The astronauts who wake up would be technological and cultural anachronisms, people from a bygone era suddenly thrust into a world that might seem like magic or madness to them. They would be entirely dependent on a civilization that may view them as curious relics, fascinating artifacts from history, or perhaps even as a burdensome responsibility requiring immense resources to support. Their skills, knowledge, and cultural references would be centuries out of date, making it incredibly difficult for them to integrate or contribute meaningfully. They might be seen as living museums, but not as functional members of that future society. This dependency is a critical vulnerability. Their survival after reanimation would hinge entirely on the goodwill and capabilities of people they have never met, from a culture they do not understand. Moreover, the medical technology required to safely reanimate them might not even exist in a usable form at the destination. While we are assuming a future society advanced enough to receive an interstellar probe, their medical priorities and technological pathways could have diverged dramatically. They might have moved beyond biological bodies entirely, embracing synthetic forms or digital consciousness, and thus lack the specific expertise or equipment for reviving cryopreserved humans the techniques for safely rewarming a vitrified body, removing cryoprotectants, and restarting metabolic functions without causing damage are incredibly complex, and that knowledge could have been lost or deemed obsolete. Alternatively, their medical technology might have evolved in unpredictable ways, using methods we cannot conceive of today that are incompatible with our preservation process. For instance, they might use nanites or bioprinters for repair. But if our vitrification process is not designed to interface with those systems, it could lead to failure. This creates a deeply ironic paradox. A civilization that is sufficiently advanced to successfully reanimate these astronauts would, by definition, be incredibly technologically sophisticated. But such a civilization would likely have also developed far more efficient means of space travel, such as faster-than-light propulsion or matter transmission, rendering the centuries-long cryonic journey utterly obsolete. Why would they bother with slow, generation-spanning ships when they can travel almost instantly? The very success of cryonics in preserving the astronauts could be negated by the societal progress it was meant to bridge. The mission becomes a quaint, expensive anachronism, a solution to a problem that future technology has already solved in a much better way. The astronauts might awake only to find that their epic journey was unnecessary, that everyone back on Earth has already arrived centuries earlier through superior means. This temporal disconnect also raises questions about the mission's purpose. Was it for colonization? If so, the target world might already be fully settled by humans or other beings who arrived much sooner. Was it for exploration? Future AI probes or advanced sensors could have already mapped the entire system in exquisite detail. The astronauts' roles and identities, so carefully preserved, could become meaningless in this new context. Their memories of Earth from centuries past would be of a world that no longer exists, and the people they knew would be long dead, making their awakening a profoundly lonely and disorienting experience. They would face an unimaginable psychological burden, grappling with a sense of irrelevance and loss on a scale no human has ever experienced. Furthermore, the ethical and social frameworks of the future society might be completely alien. Concepts of individuality, authority, or even life itself could have been redefined. The astronauts, products of their time, might hold values or beliefs that are considered primitive or offensive in the future, leading to cultural clashes or even persecution. Their very presence could be disruptive, raising difficult questions about resource allocation, historical responsibility, and the rights of revived individuals. Would they be treated as citizens, as refugees, or as property of the state? The legal and moral status of a person revived from centuries past is a grey area we have not begun to address. From an economic perspective, the cost of caring for these historical individuals could be significant, and a future society might be unwilling to bear that burden, especially if they see little value in it. The mission's success, therefore, does not end with safe arrival and reanimation. It hinges on a compatible and willing future civilization. This paradox forces us to reconsider the entire rationale for cryonic space travel. It highlights the immense risk of betting on a specific technological future that may not materialize as we hope. Perhaps the only viable missions are those where the destination is an uninhabited world and the reanimation technology is sent along with the astronauts. A fully self-contained system that can revive and support them without external help. But developing such autonomous medical technology is even more challenging than the cryonics itself. It would require robots or AI capable of performing incredibly complex surgical and biological procedures after centuries of dormancy, a feat that pushes the boundaries of reliability and artificial intelligence. Alternatively, we might need to send along a full record of our current technology and cultural knowledge, a kind of time capsule instructions, But that assumes the future civilization can and will decipher and use it. The temporal paradox is thus a fundamental limitation that cannot be solved by engineering alone. It is a reminder that space exploration is not just a physical challenge, but a temporal one, entangled with the unpredictable flow of history and progress. For the astronauts, suspended in cold sleep, time effectively stops. But for the universe outside, it marches relentlessly forward. Their journey is a leap of faith not only in technology, but in the very trajectory of humanity. Will the future be a place where they are welcomed and understood? Or will it be a foreign and indifferent landscape where they are lost relics? This uncertainty casts a long shadow over the entire endeavour, suggesting that the greatest obstacle to cryonic space travel may not be the preservation of the body, but the preservation of its meaning and purpose across the vast gulf of time. As we dream of reaching the stars, we must also dream of the world that will be there to greet us, and hope that it is one where our sacrifices and efforts are still valued. Without that, the most perfect cryonic preservation is nothing but a beautifully crafted message in a bottle, thrown into the ocean of time, with no guarantee that anyone will be there to read it, or that they will care if they do. Faced with the dizzying temporal paradoxes and engineering nightmares of full cryonic suspension, it's worth stepping back and asking if there's a more biologically grounded path. One that doesn't involve turning the body into a glassy statue, but instead works with our innate physiology. This is where the concept of induced hibernation, or torpor, enters the conversation as a compelling and potentially more realistic alternative for long-duration space travel. Instead of deep freezing, which battles fundamental physics, scientists are exploring how to put humans into a state of dramatically depressed metabolism, similar to bears or ground squirrels during winter. This wouldn't be the centuries-long sleep of science fiction, but a managed, reversible slumber lasting for months or perhaps a few years, making it ideal for journeys within our own solar system. The core idea is to significantly lower the body's metabolic rate, thereby drastically reducing the need for oxygen, food, and water, while also minimizing waste production. Imagine a crew module where astronauts are in a deep dot, drug-induced sleep, their heart rates slowed to just a few beats per minute, their breathing almost imperceptible, and their body temperature lowered to something akin to mild hypothermia, but in a controlled and safe manner. This approach completely sidesteps the two biggest villains of cryonics: the formation of lethal ice crystals and the toxic effects of cryoprotectant chemicals. There is no freezing involved, so there's no risk of cells being shredded by expanding ice. There is no need to pump the body full of poisonous antifreeze, so the danger of chemical overdose and osmotic shock is eliminated. The preservation is purely metabolic. You are slowing the engine of life down to a gentle idle, not shutting it off and hoping to restart it later. This makes the biological problem entirely different and, in many ways, more manageable with our current understanding of physiology. The primary benefit for a space mission is the immense savings on resources. A hibernating crew would require far less food and water, reducing the mass and volume of supplies that need to be launched from Earth. Their lowered metabolism would also produce less carbon dioxide and other waste products, simplifying the life support systems needed to recycle air and water. The spacecraft itself could be smaller and more efficient, as you wouldn't need the massive, multi-layered cryogenic capsules designed to last millennia. Furthermore, the psychological benefits are substantial. The crew would not experience the monotonous and mentally taxing passage of time. For them, the journey would feel like a single long night's sleep, avoiding the issues of boredom, isolation, and interpersonal conflict that can plague crews on long missions. From an engineering perspective, maintaining a stable, cool temperature for a hibernating human is a far more straightforward task than maintaining the deep cryogenic temperatures required for vitrification. You are dealing with a range around 10 to 15 degrees Celsius, not minus 196. The systems to achieve this are less energy intensive and more reliable over the shorter timescales of solar system travel. However, inducing a safe and sustainable hibernation state in humans is a massive physiological challenge. While some animals are natural hibernators, humans are not. Our bodies are not evolutionarily designed for prolonged torpor. The most immediate problem is the maintenance of muscle and bone mass. Even in a state of slowed metabolism, prolonged inactivity leads to muscle atrophy and bone demineralization. On the International Space Station, astronauts combat this with rigorous daily exercise. But that isn't an option for someone in a hibernation pod. Researchers are investigating ways to mitigate this, such as using electrical stimulation to contract muscles or administering drugs that signal the body to preserve tissue. Another major hurdle is preventing the formation of blood clots, which can occur when circulation is greatly reduced. The immune system also becomes suppressed during torpor, raising the risk of infections taking hold. Then there's the brain. We need to ensure that the drugs or techniques used to induce hibernation do not cause neurological damage or impair cognitive function upon awakening. The process of inducing and maintaining this state is complex. It likely involves a cocktail of drugs that target the central nervous system to lower the metabolic set point, combined with precise environmental controls for temperature and humidity. The astronauts would need to be monitored constantly for vital signs, and the systems would need to be able to automatically administer fluids, nutrients, and medications to maintain homeostasis. Rewarming from hibernation is also a critical phase that must be carefully controlled to avoid shock to the system. Despite these challenges, induced hibernation is an active area of research, not just for space travel but also for medical applications here on Earth, such as buying time for patients undergoing major surgery or trauma. For space missions to Mars or the outer planets, hibernation represents a pragmatic compromise. A journey to Mars takes around 6 to 9 months. Hibernation could make that time pass in a blink for the crew, reducing their psychological stress and the mission's resource load. It serves as a technological precursor to full cryonics, allowing us to develop the systems for managing unconscious crews on long journeys without having to solve the infinitely harder problem of freezing and thawing. It bridges the gap between science fiction and our current biological limitations, offering a near-term solution that could be tested and implemented within decades, not centuries. While it doesn't offer the promise of interstellar travel to other star systems, it perfectly addresses the needs of exploring and establishing a presence within our own celestial neighbourhood. It turns a voyage to Jupiter's moons from a grueling multi-year endurance test into a manageable mission where the crew is fresh and ready upon arrival. In many ways, pursuing hibernation is a smarter first step, building our knowledge and technology in incremental stages. We learn to put people into a deep sleep and wake them safely. We solve the problems of muscle wasting and immune function in a low metabolism state. And we gain invaluable experience in automated medical care for unconscious patients. All of this knowledge would be directly applicable if we ever decide to take the next, much larger step towards true cryonic suspension for journeys beyond the solar system. For now, induced hibernation stands as the most plausible path forward for human stasis in space. A solution that works with the body we have rather than trying to fundamentally alter its physical state. It acknowledges the immense difficulties of cryonics while providing a viable, exciting alternative that could revolutionize how we conduct human exploration of the planets next door. It is a testament to the idea that sometimes the most advanced solution is not the most extreme one, but the one that most elegantly aligns with the principles of biology as we already understand them. The discussion about the technical feasibility of hibernation or cryonics inevitably leads us to a much more difficult and profound set of questions. Ones that are not about engineering or biology, but about morality, consent, and the very definitions of life and death. The decision to subject a human being to cryonic suspension, an unproven technology that by current medical standards results in certain death, is an ethical minefield of staggering complexity. It forces us to confront scenarios for which our existing legal and ethical frameworks are utterly unprepared. At the heart of this dilemma is the issue of informed consent. How can a person give truly informed consent for a procedure where the potential consequences are completely unknown? We can explain the risks of ice crystal formation, cryoprotectant toxicity, and rewarming fractures, but we cannot possibly describe what the experience of being revived centuries in the future would be like, or even if it is possible. The astronaut is being asked to consent to a form of death with an unproven, speculative chance of a future life. A gamble where the odds are fundamentally incalculable. This stretches the concept of informed consent to its breaking point. Then there is the question of authority. Who has the right to make this decision for a crew? Is it a collective choice made by the astronauts themselves? Is it a command decision made by a mission director on Earth? Or is it a policy enacted by a government or space agency? If an astronaut becomes incapacitated during the mission and cannot consent, does the mission protocol allow for involuntary cryopreservation? This moves the discussion into terrifying territory. Would subjecting a crew member to this procedure against their will be seen as a heroic act of desperation, a last-ditch effort to preserve life? Or would it be considered a criminal act of negligence or even manslaughter? The line between pioneering medicine and unlawful experimentation becomes dangerously thin. The cost of such a mission also raises serious ethical concerns about resource allocation. The astronomical funds required to develop the technology and launch a cryonic interstellar mission could be directed towards solving pressing problems on Earth, such as disease, poverty, or climate change. Is it ethically justifiable to spend such vast sums on a highly speculative mission that benefits a handful of individuals, if it benefits anyone at all, when that money could save or improve millions of lives today? This is not a new question in space exploration, but it is amplified to an extreme degree when the mission spans centuries and the chance of success is unknown. Proponents might argue that the technological spin-offs and the expansion of human knowledge justify the cost, but detractors would see it as a profound misallocation of resources on a grand scale. The ethical debate also surrounds the very nature of the procedure. From a contemporary legal and medical perspective, a person who undergoes cryopreservation is dead. Their heart has stopped, their brain activity has ceased, and they are legally declared deceased. Cryonics is an intervention performed on a corpse. Yet, the entire premise of the field is that this state of death is reversible under future technology, challenging our core definitions of what it means to be dead. Are these astronauts pioneers, or are they corpses on a one-way trip? This redefinition has massive implications for everything from life insurance and inheritance to marital status and criminal law. If an astronaut is revived in 500 years, are they still married? Who inherits their property? Are they considered a citizen of their original country or a stateless person? The legal chaos would be unprecedented. Furthermore, the selection process for such a mission is fraught with ethical perils. Who gets chosen for this potential shot at a future life? Is it based on skills, health, wealth, or a lottery? The creation of a small, Elite group chosen for potential immortality, while the rest of humanity faces certain mortality raises issues of inequality and justice that could fracture societies. The psychological impact on the crew must also be considered. Even with consent, the mental burden of choosing to undergo a process that is indistinguishable from death, with the hope of awakening in an unknown future, is immense. The anxiety and fear in the moments leading up to suspension are unimaginable. And as we discussed earlier, the psychological trauma upon awakening could be devastating. Finally, there is the ethical responsibility of the future society that might revive them. Do they have an obligation to care for these people from the past? What if their revival leads to suffering? The astronauts become the ultimate vulnerable population, entirely at the mercy of a future civilization's ethics and resources. The ethical landscape of cryonics forces us to look beyond the how and confront the if and the who. It compels us to question our values, our definitions of life and death, and our responsibilities to both the present and the future, before any capsule is ever built. We must have a global conversation about these issues. The challenge is not merely to overcome the biological and physical barriers, but to decide whether, in doing so, we are upholding our deepest ethical principles or compromising them in the name of progress. The decision to freeze a human being for space travel is not just a technical milestone. It is a philosophical Rubicon, and crossing it would change humanity's relationship with mortality, time, and itself forever. Without a robust ethical framework, the technology, no matter how advanced, could represent a step backward for our civilization, creating new forms of inequality and moral ambiguity that we are ill-equipped to handle. The cold vacuum of space is not the only void we must navigate. We must also find our way through the uncharted territory of our own moral conscience. But after wrestling with the heavy ethical questions of who gets to decide and what constitutes informed consent, we must return to the brutal, practical mechanics of how this would actually work. And one of the most immediate and grueling technical hurdles is achieving uniform perfusion. This is the logistical nightmare of injecting cryoprotectants throughout the entire human body in a way that is both rapid and perfectly even, ensuring that every single cell, from the neurons in your brain to the fibroblasts in your skin, receives the precise concentration of these protective chemicals before cooling begins. Imagine trying to force a thick, syrupy liquid through every single pipe and capillary in a massive, complex city all at once, without any blockages, air bubbles, or uneven distribution. That is essentially the task at hand, and the human circulatory system is far from a perfect, symmetrical network. It has zones of different flow rates, tiny capillaries that are thinner than a human hair, and natural barriers that resist penetration. The most famous of these barriers is the blood-brain barrier, a highly selective membrane that protects the brain from many substances in the blood. This barrier, while essential for everyday health, becomes a formidable enemy during cryopreservation because it can slow down or prevent the cryoprotectants from reaching the brain cells, leaving them vulnerable to ice formation. If even a small region of the brain is underperfused, it could lead to localized freezing that destroys the very neural connections that hold memory and identity, rendering the entire preservation effort pointless. The need for speed is equally critical. The process must be completed quickly after clinical death to minimize ischemic damage, which is the injury caused by lack of oxygen. Every second that passes without oxygen, cells are dying, and in the brain. This damage becomes irreversible after just a few minutes. So, you are in a race against time. You need to perfuse the entire body thoroughly and uniformly, but you also have to do it fast. This creates a terrible conflict. if you pump the cryoprotectants in too quickly to save time, you risk causing osmotic shock, where water rapidly rushes out of cells due to the high solute concentration, leading to cellular shrinkage and damage before freezing even begins. If you go too slowly to avoid shock, you allow more ischemic damage to accumulate. Finding the perfect perfusion protocol is a bioengineering puzzle of nightmarish proportions. The problem is further compounded by the sheer scale of the human body. Protocols that work beautifully in small animals, like mice or rats, often fail miserably when scaled up to humans. This is not a simple linear scaling. It is a problem of volume, surface area, and time. A mouse has a much simpler circulatory system and a much smaller volume to perfuse. You can get the cryoprotectant to every cell in a mouse relatively quickly. But a human body is orders of magnitude larger and more complex. The time it takes for the perfusion solution to travel from the heart to the most distant capillaries is much longer. And during that time, the solution might start to settle or diffuse unevenly. Different organs also present unique challenges. The liver, for example, is a highly vascular organ and might perfuse relatively easily, while dense tissues like tendons or bones might be much harder to saturate. The kidneys, with their intricate filtering systems, might trap or alter the cryoprotectants. The heart muscle itself has a high metabolic rate and could be particularly sensitive to any delays or imperfections in the process. This lack of homogeneity means that a one-size-fits-all approach does not work. A protocol that perfectly preserves the liver might be completely inadequate for the brain or the skin. This is why achieving uniform perfusion is not just a medical challenge. It is a profound problem in fluid dynamics within a living, albeit dying, biological system. Researchers are tackling this problem from multiple angles. One approach is to use sophisticated pumps and monitoring systems that can precisely control the pressure and flow rate of the cryoprotectant solution, perhaps using pulsatile flow to mimic the heart's natural pumping action and help push the solution into smaller vessels. Another idea is to use multiple injection sites throughout the body instead of relying solely on the major arteries, to try and achieve a more even distribution from several points at once. Scientists are also experimenting with different types of cryoprotectant cocktails that might have better penetration properties or be less viscous, allowing them to flow more easily through the microscopic capillaries. Some are even investigating the use of chemicals that can temporarily make the blood-brain barrier more permeable, although this carries its own risks of causing damage. The goal is to create a perfusion protocol that is like a perfectly choreographed dance, where every step is timed and measured to ensure that the protective chemicals arrive at every cell at the same moment and in the right concentration. In the context of space travel, these challenges are magnified. The perfusion equipment on a spacecraft would need to be fully automated and incredibly reliable. It would have to initiate the process the moment clinical death is confirmed, with no human intervention. Furthermore, the microgravity environment could wreak havoc on perfusion dynamics. On Earth, gravity helps with fluid distribution, but in zero-G, fluids behave differently. Cryoprotectants might not perfuse evenly. They could pool in certain areas due to the lack of gravitational pull, leading to oversaturation in some regions and underprotection in others. This could create pockets where ice crystals form undetected, sabotaging the entire vitrification process from within. The capsule would need advanced sensors to monitor the perfusion in real time, perhaps using imaging techniques to track the flow of the solution and adjust the parameters on the fly. But even with the best technology, an imperfect perfusion means guaranteed destruction of parts of the body. You could end up with a brain that is perfectly preserved in some lobes but turned to mush in others, or a liver that is vitrified while the kidneys are crystallized. This non-uniform destruction would make reanimation impossible, as the body would not be able to function as an integrated system. Therefore, the challenge of uniform perfusion is a gatekeeper. It is the first major physical hurdle that must be cleared after the decision to proceed has been made. Without solving this, all the other advances in cooling and rewarming are irrelevant. It is a problem that requires a deep understanding of both the large-scale engineering of fluid systems and the microscopic world of cellular biology. For astronauts undergoing this procedure, their fate hinges on the perfection of this initial, chaotic process. It is a stark reminder that for all the high-concept talk of interstellar travel and future revival, the success of cryonics often comes down to solving a very messy, very immediate, and very wet problem of getting a chemical soup to every nook and cranny of a human body in a matter of minutes. It is a task that demands precision, speed, and a level of control over biology that we are still striving to achieve. As research continues, each small improvement in perfusion techniques for organ transplantation brings us a little closer, but the leap to a whole human remains a distant goal. For now, the challenge of uniform perfusion stands as one of the most formidable obstacles on the path to making cryonic space travel a reality, a problem where failure is not an option, but success is incredibly difficult to guarantee. So, after overcoming the immense challenge of achieving uniform perfusion and successfully vitrifying the body, we might think the hardest part is over. But in reality, a new and even more patient enemy emerges: the relentless passage of time itself. The long-term stability of a vitrified biological system is a problem that operates on a timescale we can barely comprehend, where even in the deep cold of cryogenic storage, physical and chemical processes do not come to a complete halt. This isn't about surviving for a few decades. It's about remaining intact for centuries or even millennia during an interstellar journey. And the vitrified state, while stable in the short term, is not a permanent one. The primary threat to this stability is a phenomenon called devitrification. Think of the vitrified body as a supercooled liquid in a solid, glass-like state. Over incredibly long periods, the molecules within this glassy matrix can slowly gain enough energy to start moving and rearranging themselves into a crystalline structure. This is devitrification, the spontaneous formation of ice crystals within the previously clear, vitrified tissue. It's a slow, insidious process that doesn't require any external trigger other than time and the inherent instability of the glassy state. Even at temperatures as low as -196 degrees Celsius. Atomic and molecular vibrations never truly cease due to quantum mechanical effects. These tiny, constant movements can, over thousands of years, provide just enough energy for water molecules to break free from their amorphous arrangement and snap into the rigid, destructive lattice of ice. This means that a body perfectly preserved at the start of a 1,000-year journey could, upon arrival, be filled with the very ice crystals that the vitrification process was designed to prevent, effectively turning the preservation into a slow-motion failure. The rate of devitrification depends on several factors, including the specific composition of the cryoprotectant cocktail, the integrity of the vitrified matrix, and the storage temperature. Even minor impurities or imperfections in the vitrification can act as nucleation sites, accelerating the crystallization process. Furthermore, the different tissues in the body, with their varying water and protein content, might devitrify at different rates, leading to uneven degradation where some organs become crystalline while others remain glassy, causing internal stresses and structural damage. Another silent and unavoidable threat is background radiation. Space is filled with high-energy cosmic rays and other forms of ionizing radiation. On Earth, we are shielded by the atmosphere and magnetic field, But in deep space, a cryogenic capsule is constantly bombarded. This radiation can penetrate the capsule and the vitrified body, damaging biological molecules like DNA, proteins, and lipids. While metabolic activity is paused, the physical interaction between radiation and molecules still occurs. When a high-energy particle smashes into a DNA strand, it can cause breaks or mutations. In a living cell, repair mechanisms would fix this damage, but in a vitrified state, there are no active repairs. Over centuries, this damage accumulates. Imagine the genetic code in every cell gradually being chipped away, with mutations piling up. Upon revival, this could lead to widespread cellular dysfunction, a high risk of cancers, or the failure of critical systems to reboot properly. The brain's connectome, the delicate wiring that stores memories and personality, is particularly vulnerable. Radiation-induced damage could corrupt synaptic structures or damage the DNA within neurons, leading to cognitive deficits or complete loss of identity. The cumulative effect of radiation over millennia is a largely unknown and terrifying variable. We have no long-term data on how vitrified biological matter withstands this constant assault. The problem is that these processes are so slow that they are impossible to observe directly in a human lifetime. All our knowledge of vitrification stability comes from experiments lasting years, maybe a few decades at most. Extrapolating that to thousand-year timescales is pure speculation. We are relying on models and theories, but we cannot be certain. Materials science tells us that all glasses have a tendency to crystallize over sufficient time, and biological glass is likely no exception. The question isn't if devitrification will happen, but when, and whether that time frame is longer than the intended journey for a mission to a nearby star system, which could take tens of thousands of years. The risk is astronomically high. Even if devitrification is slow, the radiation damage would be significant. This introduces a cruel paradox. The longer the journey, the more likely the preservation will fail. But the longer journeys are precisely the ones where cryonics is most needed. Ensuring stability over geological timescales is a challenge entirely different from preservation for a few decades. It requires more than just a good freezer. It requires a fundamental understanding of material science at cryogenic temperatures over epochs. Engineers would need to design capsules that not only maintain temperature but also provide significant radiation shielding. This could involve thick layers of water or hydrogen-rich materials, or even active magnetic shielding. But these solutions add mass, complexity, and potential failure points. Moreover, the capsule itself must withstand material degradation over millennia. Metals can become brittle, seals can fail, and insulation can degrade, all of which could lead to temperature fluctuations that accelerate devitrification. The reliability engineering for such a capsule is unprecedented. We have never built anything that must function flawlessly for such a long time. The Voyager probes are a few decades old and are already showing signs of age. A millennia-long mission requires a level of durability we can hardly imagine. From a biological perspective, we don't know if some tissues are more susceptible to long-term degradation than others. The brain, with its high lipid content, might be more vulnerable to radiation-induced lipid peroxidation, even in a vitrified state. Connective tissues might become brittle. The slow loss of molecular integrity could mean that even if the body is rewarmed successfully, the cells might not function correctly because their fundamental machinery has been subtly damaged over the centuries. This is why long-term stability is often the overlooked showstopper in discussions about interstellar cryonics. We focus on the dramatic challenges of freezing and thawing, but the quiet, patient work of time and physics in the interim may be the ultimate undoing. It forces us to consider whether cryonics is a viable solution for anything beyond relatively short-term storage. Perhaps it could work for journeys within a human lifetime, but for true generations-spanning voyages, the technology may need to be coupled with ongoing maintenance or repair systems that we cannot yet conceive. Some theorists suggest that future nanotechnology could periodically scan and repair the vitrified bodies during the journey, correcting molecular damage and preventing devitrification. But this is speculative and relies on technologies that do not exist. For now, the long-term stability of a vitrified human remains an unproven and deeply uncertain aspect of cryonics. It is a reminder that preserving life is not just about stopping time in a moment, but about defending that moment against the inexorable forces of entropy and decay across timescales that dwarf human history. For astronauts embarking on a millennia-long journey, their fate depends not only on the technology of their time, but on its ability to endure an almost infinite night, cold and silent, where the slow creep of physical change could erase them long before they reach their destination. This challenge humbles our ambitions and underscores that space travel is not just a spatial problem, but a temporal one, where the enemy is time itself, and we are only beginning to learn how to fight it. But after meticulously solving the colossal problems of long-term biological stability, ensuring that the physical body and brain arrive at their destination perfectly preserved against the ravages of time and radiation, we are faced with what might be the most human of all challenges: the profound psychological shock of awakening. The mental and emotional state of an astronaut reviving after centuries in stasis is a critical factor that could determine the ultimate success or failure of the entire mission. And it is an aspect often overshadowed by the more tangible technical hurdles. Imagine the disorienting, terrifying moment of consciousness returning, not in a familiar hospital room or even on a recognizable spaceship, but in a medical facility on a world you have never seen, surrounded by technology you cannot comprehend, and greeted by people whose language, customs, and even physical appearance might be alien to you. The first realization would likely be a staggering sense of loss and grief on an unimaginable scale. Every single person you ever knew and loved, family, friends, colleagues, has been dead for hundreds of years. The world you called home, with its cultures, nations, and daily life, exists only in history books. You are a living relic, a ghost from a past era, and the weight of that solitude would be crushing. This isn't just homesickness. It is a fundamental severing from every emotional and social anchor that defined your existence. The psychological trauma of such a loss could be paralyzing, leading to severe depression, anxiety, or a complete withdrawal from reality. The astronaut would need to mourn not just individuals, but an entire world and a way of life that is gone forever. This grief would be compounded by a deep and pervasive sense of disorientation. The future society would be technologically and culturally advanced in ways that seem like magic. Communication might involve direct neural interfaces. Transportation could be instantaneous, and social structures could be based on principles we can't currently fathom. The astronaut would feel like a child, or worse, an primitive intruder, struggling to understand basic concepts and navigate a society where they are utterly incompetent. Their hard-earned skills and knowledge as a space explorer might be completely obsolete, rendering them dependent and stripping them of their purpose and identity. This loss of agency and competence is a massive blow to self-esteem and mental well-being. The extreme isolation is another devastating factor. While they might be surrounded by people, the astronaut would be profoundly alone in a way no human has ever experienced. There is no one who shares their cultural context, their memories, their jokes, or their values. They cannot have a simple conversation about their past without explaining centuries of history. They are a singular data point from a bygone era. And this unique status creates an unbridgeable gap between them and everyone else. This could lead to intense loneliness, a feeling of being a specimen under observation rather than a person, and a deep-seated identity crisis. Who are you when your entire frame of reference is gone? The very core of your personality, shaped by your time and experiences, might feel irrelevant or even maladaptive in this new world. The potential for psychological disorders is high. Post-traumatic stress disorder from the awakening experience itself is a real possibility. The shock could trigger psychotic breaks, severe anxiety disorders, or catatonia. The astronaut might struggle with trust, paranoia about their new environment, or an overwhelming desire to return to stasis to escape the unbearable reality. Their mental health would be as fragile and critical as their physical health upon revival. A technically revived but psychologically broken astronaut is a mission failure. They would be unable to contribute, to adapt, or to find any meaning in their new existence. Preparing for this psychological ordeal is therefore as important as developing the cryonic technology itself. How do you psychologically prepare a person for an experience that is, by its very nature, beyond human comprehension? Pre-mission training would need to involve intense psychological conditioning, focusing on resilience, adaptability, and coping strategies for extreme loss and change. It would involve exposing them to speculative scenarios of future societies and training them in fundamental principles of learning and social integration. However, no amount of training can fully simulate the actual emotional impact. Upon awakening, a robust and carefully planned support system would be essential. This would involve a dedicated team of psychologists, cultural mediators, and support personnel who specialize in historical trauma and integration. The revival process would need to be gradual and controlled, allowing the astronaut to acclimate slowly to sensory input and new information. They would need a safe, controlled environment where they can learn at their own pace, without being overwhelmed. Access to historical archives about their own time might provide some comfort, but it could also deepen the sense of loss. The ultimate goal would be to help them find a new purpose and identity in this future world. Perhaps they could become teachers, sharing first-hand knowledge of a lost era, or they might be involved in further exploration, using their unique perspective as a baseline from the past. But this is a best-case scenario. The ethical responsibility of the future society is immense. They would need to commit significant resources to the long-term mental health care and social integration of these individuals, treating them not as curiosities but as vulnerable refugees from time. The success of the cryonic mission, therefore, doesn't end with biological revival. It only begins there. The psychological well-being of the astronaut is the final, and perhaps most delicate, piece of the puzzle. It forces us to consider not just if we can revive someone, but whether we should, if we cannot guarantee them a life worth living. The mental landscape of awakening is a frontier as vast and unknown as space itself, and navigating it requires a depth of compassion and understanding that must be developed in tandem with the technology of preservation. For the astronaut, the journey through time is not just a physical passage, but an emotional odyssey that will test the very limits of human resilience. And we must be ready to guide them through the profound darkness of being a stranger in their own future. But after considering the profound psychological shock of awakening centuries in the future, we must rewind the entire process and confront a much more immediate and brutal reality. The damage that occurs in the precious minutes between the moment an astronaut's heart stops and the moment cryopreservation is fully achieved. This period, known as the ischemic window, is a race against biological time where every second counts, and failure to act instantly can render all subsequent preservation efforts utterly futile. Ischemia, the lack of oxygenated blood flow, triggers a rapid and catastrophic cascade of cellular damage throughout the body, but it is especially devastating for the brain. Brain cells are exquisitely sensitive to oxygen deprivation. Within mere minutes of the heart stopping, neurons begin to die in large numbers, leading to irreversible damage that would erase memories, cognitive functions, and the very identity of the individual. This isn't a slow process. It's a swift and brutal dismantling of the delicate electrochemical balance that sustains consciousness and life itself. The core problem is that cryopreservation is not a magical pause button that can be pressed at any time. It is a complex medical procedure that must be initiated under controlled conditions to have any chance of success. In the context of a space mission, where clinical death might occur due to equipment failure, accident, or planned protocol, the response must be nearly instantaneous. The current reality is that even under ideal terrestrial conditions, minimizing ischemic damage is a monumental challenge. When blood flow ceases, cells are starved of oxygen, and their energy production grinds to a halt. Without oxygen, cells cannot produce adenosine triphosphate, which is the primary energy currency for all cellular processes. This energy failure causes ion pumps in cell membranes to stop working, leading to an influx of calcium and sodium ions and an efflux of potassium ions. This ionic imbalance causes cells to swell and triggers the release of glutamate, an excitatory neurotransmitter that in high amounts becomes toxic, overstimulating and killing neurons in a process called excitotoxicity. Meanwhile, anaerobic metabolism kicks in, producing lactic acid and dropping the intracellular pH, which further damages enzymes and cellular structures. Free radicals, highly reactive molecules, also build up, causing oxidative stress that attacks lipids, proteins, and DNA within 5 to 10 minutes. This cascade can cause widespread, irreversible brain damage. For other organs, the timeline might be slightly longer, but the heart, kidneys, and liver also suffer severely from ischemia. This means that by the time a body is cooled and perfused with cryoprotectants, the cellular machinery may already be so compromised that even perfect vitrification would be preserving an extensively damaged structure. The goal of cryonics is to preserve the pattern of the brain with enough fidelity to allow future revival. But ischemic damage shreds that pattern beyond recognition before preservation even begins. Therefore, the entire success of a cryonic mission hinges on slamming this ischemic window shut as quickly as humanly and technologically possible. This requires a paradigm shift in how we approach death in space. Instead of treating clinical death as an endpoint, it must be treated as a medical emergency that triggers an automated, integrated response from the spacecraft itself. The capsule cannot be a passive storage unit. It must be an active medical device capable of initiating cryopreservation procedures within seconds of detecting cardiac arrest or catastrophic vital sign failure. This implies a level of automation and system integration that borders on science fiction today. Imagine sensors embedded throughout the astronaut's suit or cabin that monitor heart rate, brain activity, and blood oxygenation in real time. The moment these sensors indicate legal death according to predefined criteria, the system would spring into action without any human intervention. The first step would be to initiate cardiopulmonary support or perhaps total body perfusion with a specialized solution designed to mimic oxygenated blood, buying a few critical extra minutes by mechanically circulating oxygen and nutrients. However, this is only a temporary measure. The real solution is to begin the cryoprotectant perfusion and cooling process immediately. This means the capsule must have integrated catheters or ports connected directly to the astronaut's major blood vessels, perhaps through surgically implanted access points established before the mission. Upon detection of death, pumps would activate, flushing the body with a cold, oxygenated solution to rapidly lower core temperature and reduce metabolic demand, followed swiftly by the introduction of the cryoprotectant cocktail. The entire perfusion process, which normally might take hours in a controlled lab setting, would need to be compressed into minutes to outpace the ischemic cascade. The cooling rate must be extremely rapid to quickly reach temperatures where metabolic activity is negligible, but not so fast as to cause thermal shock or uneven freezing. This is a bioengineering nightmare. The system must manage fluid dynamics, pressure control, and temperature gradients with precision, all while compensating for the microgravity environment of space, which could affect how fluids flow and distribute through the body. Furthermore, the cryoprotectant solution itself might need to be pre-cooled and ready to inject, and the protocols for its introduction must be optimized to prevent osmotic shock during this accelerated timeline. The development of such emergency protocols is an area of active research in cryobiology, but applying them to humans in space adds layers of complexity. For instance, what if the cause of death is traumatic, like a hull breach or physical injury? The system would need to be robust enough to handle various scenarios, perhaps involving robotic arms or automated surgical systems to secure vascular access if needed. The reliability of these systems is paramount. A single failure in a pump, sensor, or software algorithm could doom the entire preservation effort. Moreover, the ethical and legal dimensions are profound. Initiating such an invasive procedure automatically upon legal death requires explicit, informed consent from the astronaut before the mission. And even then, it pushes the boundaries of medical ethics. Is it ethical for a machine to take over a human body the moment death is declared? This question becomes even more poignant in space, where communication delays with Earth might prevent any real-time human oversight. The ischemic problem forces us to redefine the very concept of death in the context of cryonics. Instead of being a permanent state, death becomes a process, and the goal is to interrupt that process before it causes irreversible information theoretic death, the point where the brain's structure is so damaged that the mind cannot be recovered. Minimizing ischemic damage is therefore the first and most critical barrier in the cryonic pipeline. If we cannot solve this, then all the advances in vitrification, rewarming, and long-term storage are for naught, because the material being preserved is already a corrupted version of the original person. For astronauts on interstellar missions, their hope of future life depends on winning this race against the clock in the first few minutes after their heart stops. It is a stark reminder that the most advanced technology is useless if it cannot be deployed instantly when it matters most. The solution lies not only in cryobiology, but in the seamless integration of medicine, robotics, and artificial intelligence into a system that can act with speed and precision beyond human capability. As we look to the stars, we must also look to these critical first moments, ensuring that the journey through time begins with a fight for life, not a surrender to decay. The ischemic problem is the gatekeeper to the frozen frontier, and overcoming it is the first, non-negotiable step toward making cryonic space travel a reality. After navigating the critical ischemic window and successfully initiating the cryopreservation process, we must now confront a biological truth that expands the scope of the challenge exponentially. The human body is not a singular entity, but a vast, walking ecosystem. We are not just preserving an astronaut. We are attempting to preserve an entire microscopic civilization that lives within them, known as the microbiome. This complex community of trillions of bacteria, fungi, viruses, and other microorganisms, primarily housed in the gut, is not a passive passenger. It is an essential, symbiotic partner crucial for our health and survival. The cryopreservation process, designed for human cells, would almost certainly be a massacre for the vast majority of these microbial inhabitants. These microorganisms are not as robust as human cells to the immense physical and chemical stresses of vitrification. The high concentrations of cryoprotectants that our cells might barely tolerate would be utterly lethal to most gut bacteria. The freezing and thawing process itself, even with vitrification, would likely rupture the delicate cell walls of countless microbial species. The result upon revival would be an astronaut with a sterile or severely depleted gut microbiome, and this presents a monumental medical challenge that could undermine the entire mission. The gut microbiome is not incidental. It is a functional organ. It plays an indispensable role in digesting food, synthesizing essential vitamins like B and K, training and regulating the immune system, and protecting against pathogenic invaders. Without a healthy, diverse microbiome, the revived astronaut would be incredibly vulnerable. They would likely suffer from severe malnutrition, as their body would be unable to properly break down and absorb nutrients from food. Their immune system, which developed in concert with these microbes, would be profoundly dysregulated, potentially leading to autoimmune disorders where the body attacks itself, or conversely, a state of severe immunodeficiency where they could succumb to infections that a healthy person would easily shrug off. Chronic inflammation, allergies, and a host of gastrointestinal diseases like irritable bowel syndrome would be a near certainty. The psychological impact of the microbiome should not be underestimated either. There is a well-established gut-brain axis, and the state of the gut microbiome can influence mood, anxiety levels, and even cognitive function. A damaged microbiome could contribute to the psychological trauma of awakening, leading to depression and mental fog. Therefore, reviving the body is only half the battle. Reviving a functional human requires reviving their internal ecosystem. This raises a profound and complex question for cryonic mission planners. Is it necessary to also preserve and reanimate the native microbiome? Or can we simply re-inoculate the astronaut with a synthetic or stored microbiome after revival? Both options are fraught with difficulty. Preserving the native microbiome would mean developing cryopreservation protocols that are gentle enough to protect both human cells and the thousands of different, fragile microbial species simultaneously. This might require entirely different cryoprotectant cocktails, cooling rates, and rewarming strategies specifically optimized for microbial survival, which could conflict with the protocols needed for human tissue. It would be like trying to freeze a coral reef and all its fish inhabitants in a single block of ice and expecting everything to survive. The requirements for the coral are different from the requirements for the clownfish. Alternatively, the mission could plan for a reboot. This would involve storing a frozen backup of the astronaut's own microbiome, collected before the mission, or using a standardized synthetic microbiome derived from healthy donors. Upon revival, the astronaut would undergo a fecal microbiota transplant or a similar procedure to reintroduce these microbes. However, this is not a simple fix. The success of such a transplant depends on the recipient's gut environment being receptive. If the gut lining has been damaged by the cryopreservation process or the period of inactivity, the new microbes might not take hold. Furthermore, the microbiome is highly personalized. Reintroducing a generic mix might not restore the intricate, unique balance that existed before, potentially leading to ongoing health issues. There is also a philosophical dimension to this. Is our identity tied to our microbiome? While we think of ourselves as a discrete human individual, we are in fact a superorganism. Our microbes influence our cravings, our metabolism, and perhaps even aspects of our behavior. If an astronaut is revived with a completely different set of gut bacteria, are they still entirely the same person? This might seem like a fringe question, but it underscores the holistic nature of what cryonics is attempting to achieve. The challenge of the microbiome forces cryobiology to shift its perspective from the preservation of an organism to the preservation of an ecosystem. It adds another layer of immense complexity to an already almost insurmountable problem. For a mission to be truly successful, the capsule must not only safeguard the astronaut's cells, but also the trillions of microscopic allies that make life livable. This could mean developing separate, miniaturized cryo-storage for microbiome samples, or engineering even more sophisticated vitrification solutions that are universally biocompatible. It certainly means that post-revival medical care must include extensive and long-term probiotic and nutritional support to rebuild this internal community from the ground up. The silent, invisible world of the gut microbiome thus becomes a decisive frontier in cryonic space travel. Ignoring it could mean reviving an astronaut who is technically alive but condemned to a life of chronic illness and dependency, a prisoner of their own sterile body. Acknowledging it expands the mission parameters to a staggering degree, reminding us that to save a human, we must also save the world within. After grappling with the intricate biological puzzle of preserving the human microbiome, we must now shift our gaze to an equally daunting challenge that exists not in the petri dish but in the ledger book: the staggering economics of funding a cryonic interstellar mission. The financial and resource requirements for such an endeavour are almost unimaginable, pushing the limits of what any single nation or even a consortium of corporations could realistically bankroll. We are not talking about the cost of a Mars rover or a lunar base. We are talking about financing a project whose ultimate results would not be seen for several centuries, making the return on investment a philosophical concept rather than a financial one. Who would pay for a mission whose success or failure would only be known to descendants living in a world 500 years from now? The development costs alone would be astronomical. The research and development for reliable human cryopreservation, the engineering of a millennium-proof capsule, the construction of a spacecraft capable of interstellar travel, and the launch itself would require trillions of dollars, euros, or whatever currency exists at the time. This is not a one-time expenditure. It is a multi-generational financial commitment. The funds needed are so vast that they rival the gross domestic product of large nations, raising immediate and serious questions about resource allocation. Is it ethically justifiable to spend such colossal sums on a highly speculative mission that might benefit a handful of individuals in the far future, when that same money could be used to address pressing terrestrial problems like climate change, poverty, disease, and education for millions of people alive today? This is a fundamental ethical and economic dilemma that any society considering such a mission must confront. Proponents might argue that the technological spin-offs from the research could benefit humanity in the near term, but detractors would see it as a profound misallocation of resources on a historic scale. The funding mechanism itself is a puzzle. A traditional corporate model based on profit and shareholder value is completely unworkable here. There are no quarterly earnings, no product launches, and no customers to sell to for centuries. A government-funded project would be vulnerable to the shifting winds of political will. What government would approve a budget line item for a project that will not deliver results until long after every current politician? Voter and taxpayer is dead, the political support for such a venture would be incredibly fragile, susceptible to budget cuts, changing priorities, and societal collapse over the centuries. This means the economic structure for the mission must be designed to transcend generations. It would likely require the creation of a self-sustaining financial trust or endowment, a massive pool of capital managed by an independent, transnational entity with a legally binding charter that spans centuries. The principal would be invested in a diverse, conservative portfolio designed for long-term growth, with only the investment income used to cover ongoing maintenance costs for the mission, such as monitoring the spacecraft's trajectory and maintaining communication systems, if any. This trust would need to be insulated from economic downturns, inflation, and political interference, a task of governance and financial planning as complex as the engineering challenges. The entity managing this trust would have to be nearly immortal, outlasting empires and economic systems. Furthermore, the mission's economy extends beyond mere money. It consumes vast physical resources, rare metals for the spacecraft, helium-3 or other fuels for propulsion, and the industrial capacity to build and launch a vessel of unprecedented scale. All these resources have an opportunity cost. They are being used for a speculative future instead of addressing present needs. The social and economic contract required is immense. It demands that the people of today make a tangible sacrifice for the potential benefit of people in the distant future, people they will never know and whose world they cannot comprehend. This long-term thinking is foreign to our current economic systems, which are overwhelmingly focused on short-term gains and electoral cycles. Another economic layer involves the destination. If the mission is to a potentially habitable world, who owns the resources there? Would the revived astronauts be representatives of an Earth-based entity that still exists? Would they be independent colonists? The legal and economic frameworks for interstellar property and resource rights are completely blank. The mission could also create a perverse economic dynamic back on Earth. The selection of the crew could lead to accusations of creating a privileged elite chosen for potential immortality, exacerbating social inequalities and potentially causing unrest. The very existence of such a project could be seen as a symbol of a society's priorities, and if those priorities are deemed misguided, it could lead to political backlash that threatens the funding over the long term. In essence, the economy of a deferred generation mission is a challenge of governance, social cohesion, and long-term vision that is every bit as complex as the challenge of cryobiology or spacecraft engineering. Without a viable and robust economic model, the mission will never leave the drawing board, no matter how many scientific breakthroughs we achieve. It forces us to evolve our economic thinking to operate on civilizational timescales, to plan for a future so distant it becomes abstract. It requires a global consensus and a commitment to a goal whose architects will never see its fruition. This is perhaps the ultimate test of our species' ability to think beyond the immediate and the personal, to invest in a legacy that belongs to all of humanity, yet one that none of us will ever personally witness. The dream of reaching the stars is not just bottled by physics and biology, it is bottled by economics. And solving this financial puzzle is a prerequisite for making the journey a reality. It is a sobering reminder that grand visions require not just scientific genius, but also enduring economic structures and a profound, collective will that can bridge the centuries. Without this, the most perfect cryonic capsule remains a fantasy, grounded not by gravity, but by the harsh realities of cost and the short-sightedness of human institutions. The balance sheet may ultimately be a more formidable barrier than the vacuum of space. faced with the seemingly insurmountable physical damage caused by current cryopreservation methods, the inevitable cracking, the cryoprotectant toxicity, the ischemic injury, many proponents of the field place their ultimate faith not in perfecting today's techniques, but in the speculative power of future nanotechnology. This belief posits that the inevitable damage caused by the freezing and thawing process will be repairable by armies of microscopic medical robots, or nanorobots, operating at a molecular level. In theory, these machines would be injected into the revived body and would perform a microscopic triage, scanning and fixing the preservation damage cell by cell, molecule by molecule. They could theoretically stitch torn cell membranes back together, carefully remove toxic cryoprotectant molecules from inside cells without causing osmotic shock, and even locate and correct fractures in DNA strands caused by radiation or the preservation process itself. This vision transforms cryonics from a preservation method into a repair-based paradigm. The goal is no longer to avoid all damage, but simply to preserve the body's structural information well enough for these future nanotechnicians to reconstruct it. It is a compelling and hopeful idea, effectively outsourcing the most difficult problems of revival to a more advanced future. However, this argument represents a colossal leap of faith, a strategic punt that moves the goalposts from present-day scientific challenges to future technological miracles. The first and most obvious problem is that this technology is purely speculative. While the concept of medical nanorobots has been a staple of science fiction for decades, the practical reality is that we are nowhere near creating such devices. We are talking about machines smaller than a human cell, capable of complex navigation, diagnosis, and repair within the incredibly dense and complex environment of human tissue. They would need their own power source, computation capabilities, and tools for molecular manipulation. The engineering challenges involved in creating just one such device are far beyond our current capabilities, let alone producing the trillions necessary to repair an entire human body in a reasonable time frame. Furthermore, the behavior of such a swarm inside a body is unpredictable and could introduce new risks. What if they malfunction? What if they trigger an immune response? What if they misidentify a molecule and cause more damage than they repair? Relying on this uninvented technology to solve the known problems of cryonics is a philosophical argument, not a scientific one. It is essentially asking us to accept a technology based on its potential rather than its proven principles. This creates a dangerous precedent for research and investment. If we believe that all damage is repairable in the future, then there is less incentive to minimize that damage in the present. Why invest immense resources and brainpower into developing the perfect vitrification protocol or a perfectly uniform rewarming method if we can just do a good enough job and let the nanobots handle the rest? This attitude could stifle innovation in the very cryobiology that is necessary to make any form of preservation viable. The nanotech fix becomes a convenient answer to every technical criticism, potentially halting progress on the ground that current problems are merely temporary. Moreover, this argument often ignores the nature of the damage itself. Some damage might be irreparable even at a molecular level. If the synaptic connections in the brain are disrupted, if the precise weights and configurations that encode a memory are lost, can any nanobot truly reassemble them? Information theory suggests that if the structural data is corrupted beyond a certain point, it cannot be recovered. A nanobot can fix a tear, but can it reliably deduce the original dots or functional state of a complex neural network that has been degraded? This is not like fixing a scratched record. It is like trying to reconstruct a burned book from the ashes. The promise of nanotechnology also overlooks a fundamental logistical issue. the interface between the macroscopic revival process and the microscopic repair. Let's say a body is rewarmed and its heart is restarted. The circulatory system is now active. How do we introduce trillions of nanobots into this system without causing immediate embolisms or overwhelming the body's functions? Would the repair process require the body to be in a second state of suspended animation while the nanobots work? How long would this molecular reconstruction take? Days? Years? The practicalities are glossed over in favour of the grand vision. This is not to say that research into medical nanotechnology is not valuable. It is a fascinating and promising field that may one day revolutionise medicine. But counting on it to solve the fundamental, show-stopping problems of cryonics is a risky and unscientific strategy. It places cryonics in the realm of belief rather than evidence-based science. The more prudent path for cryonics research is to focus on minimizing damage with the tools and knowledge we have today. The goal should be to achieve such a high level of preservation that the need for extensive molecular repair is minimized or eliminated. Every reduction in ice crystal formation, every decrease in cryoprotectant toxicity, and every improvement in rewarming uniformity is a step toward a more robust and scientifically defensible position. Breakthroughs in vitrification for organ transplantation, for instance, are tangible and valuable because they work with present-day constraints. In conclusion, while the vision of nanotechnological repair is a powerful narrative that sustains the hope of many in the cryonics community, it is a dangerous foundation upon which to build a mission as critical as preserving human lives for space travel. It is a leap of faith over a chasm of unknown science. For astronauts whose lives would depend on this technology, relying on a speculative future fix is an unacceptable risk. The focus must remain on the hard, unglamorous work of improving preservation protocols here and now, using empirical science to push the boundaries of what is possible today, rather than deferring our greatest challenges to the magic of tomorrow. The promise of nanorobots is a seductive dream, but for now, it is a dream that should not distract us from the waking reality of biological and physical constraints we must strive to overcome with the knowledge we already possess. Even if the ultimate goal of preserving astronauts for interstellar travel remains a distant and speculative dream, the relentless pursuit of that goal has already yielded a rich and tangible scientific legacy here on Earth, producing spin-off technologies that are saving lives and revolutionizing medicine today. The immense challenge of trying to cheat biological death has forced researchers to ask fundamental questions about how cells respond to extreme cold, leading to breakthroughs that have nothing to do with freezing whole people and everything to do with preserving the building blocks of life. The most successful and widespread application of this research is in the field of assisted reproductive technology. The technique of vitrification, developed to avoid ice crystal formation in cryonics, is now a routine and highly effective procedure for preserving human eggs and embryos. Before vitrification, slow freezing methods often led to ice damage, reducing the survival rates of these delicate cells. Now, with vitrification, women can freeze their eggs with a very high degree of confidence that they will be viable years later, offering freedom for those who wish to delay childbirth for medical or personal reasons. In vitro fertilization clinics worldwide rely on this technology, allowing multiple embryos from a single cycle to be stored for future attempts, drastically improving the chances of successful pregnancy and reducing the physical and emotional toll of repeated procedures. This single spin-off from cryonics research has already created families and changed lives on a global scale. Another major area of impact is in organ transplantation. Currently, a donated heart, liver, or lung can only survive outside the body for a matter of hours on ice, creating a frantic, logistical race against time to get the organ from the donor to the recipient. This narrow window limits the distance organs can travel, leads to wasted organs, and puts immense stress on surgical teams. Research driven by cryonics aims to shatter this limitation. Scientists are actively adapting vitrification techniques to preserve entire organs, seeking to extend their viable storage time from a few hours to days, or even longer. While the goal of vitrifying a whole human organ for transplantation has not yet been fully realized, significant progress is being made. Researchers have successfully vitrified and re-warmed rodent hearts and kidneys, restoring some function. The lessons learned about cryoprotectant perfusion, cooling rates, and rewarming homogeneity are directly applicable to this life-saving work. Extending organ viability would transform transplant medicine, enabling organs to be shared across continents, creating international organ banks, and saving countless lives that are currently lost due to time constraints. The study of cryoprotectants has also deepened our understanding of cellular biology under stress. Investigating how these chemicals interact with cell membranes and internal structures has provided insights into how cells manage osmotic pressure and maintain integrity in harsh environments. This knowledge is useful in fields beyond cryopreservation, such as developing better ways to store blood products, platelets, and stem cells for medical treatments. The research into preventing ice formation has even found applications in the food industry, where controlling ice crystal size is crucial for preserving the texture and quality of frozen foods, though the primary medical applications are far more significant. Furthermore, the tools and technologies developed for cryonics research, such as advanced perfusion pumps, precise temperature monitoring systems, and sophisticated mathematical models of heat transfer in biological tissues, have value in other areas of medicine and research. These engineering solutions can be adapted for targeted drug delivery systems or for improving hypothermic therapies used in hospitals to protect the brain after cardiac arrest or traumatic injury. The quest to understand and prevent damage at low temperatures pushes the boundaries of biophysics and materials science, generating knowledge that ripples out into unexpected areas. This demonstrates a fundamental truth about ambitious, frontier science. The journey itself is often as valuable as the destination. The pursuit of a grand, almost impossible goal forces innovation and problem solving at the most fundamental levels. While we may not be freezing astronauts today, the research inspired by that vision is already having a profound and positive impact on human health. It is a powerful example of how a long-term, high-risk scientific endeavour can produce a cascade of near-term, practical benefits. The legacy of cryonics research is not stored in a frozen vault waiting for the future. It is alive and well in fertility clinics helping to create new life, in transplant research labs working to extend life, and in our broader understanding of the delicate chemistry of life itself. So, while the dream of starfaring hibernating astronauts continues to drive the imagination and fuel further research, we can already appreciate the real-world dividends of that quest. The most immediate heritage of cryonics may not be the conquest of the stars, but the tangible improvement of medicine here on Earth, proving that sometimes, by reaching for the heavens, we ultimately learn how to better care for the world at our feet. The technology designed to suspend a single life for centuries is, in a beautiful twist, already being used to create and save many lives in the present, ensuring that the scientific legacy of this challenging field is both immediate and profoundly human.